Hey guys, tonight we're going to step into the ultimate time machine, setting the dial back not 1 million or even 100 million years, but 4.6 billion years. We're going to journey to the very beginning, to a time before time as we know it, to witness the birth of our planet and the alien, terrifying worlds that came long before the first dinosaur. Imagine this. You are floating in an absolute perfect blackness, but you are not alone. Before you hangs a young star, our sun. But it's not the friendly yellow orb you know, it's a violent, seething bluish-white sphere lashing out with furious solar flares. And below you is not the blue-green marble of home, it is a nightmare. Before you lies the infant Earth, a roiling, terrifying ball of magma, an entire ocean of molten iron and silicate rock glowing a deep, menacing cherry red. There is no land. There is no water. There is only a churning, boiling cauldron wrapped in a thick, choking shroud of toxic gases. From the blackness of space, a constant rain of debris, asteroids and comets left over from the solar system's formation, hammers the planet. You watch as glowing white splashes, plumes of vaporized rock, silently erupt from the magma ocean. This isn't a planet, it's a cosmic construction site, a place of pure creative violence. Over millions of years, this hellscape will be pounded, melted, and forged into the world we know. It will witness the greatest cataclysm of its life, a collision that will birth our moon. It will see the skies rain fire, and then, for millennia, rain water, until a global ocean of boiling hot, acidic water covers everything. It's in that alien ocean, in the total darkness of the sea floor, that a spark will ignite, a chemical miracle that begins the story of life. So how does a sterile ball of lava become a living world? What did this first ocean even look like? And what monsters were born in it? And how many times did life nearly get wiped out completely before a T-Rex ever took its first breath? Thanks to the detective work of geologists and paleontologists, tonight we will venture into these lost worlds together to find the answers. Frankly, if you were dropped here in this Hadean eon without your time machine, you wouldn't survive a single second. You wouldn't be crushed or drown. You'd be vaporized by the sheer heat before your brain could even register the color red. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. That small click sends a big signal to the algorithm. That long-form, serious educational content still matters. And to me, it's an incredibly meaningful show of support. Thank you so much for helping keep this channel going strong. It always fascinates me to see where you're all tuning in from. Let me know in the comments where you are in the world and what time it is for you. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're floating here, 4.6 billion years ago, and the most dramatic event of Earth's formation is happening right beneath your feet, though you can't see it. It's called the Iron Catastrophe. As the planet was being assembled from those millions of asteroid impacts, it became a homogeneous ball of melted rock and metal. But the heaviest elements couldn't stay mixed. As you watch the surface churn, trillions of tons of molten iron and nickel are sinking. They are falling in a catastrophic internal rain from the outer layers down toward the center of the planet. This process, the scientific evidence for which we see in the layered structure of our planet today, is what differentiated Earth. It's the moment our solid iron core was born, which in turn would one day generate the magnetic field that protects us from solar radiation. The air around this magma ball, if you can call it that, is a thick, crushing atmosphere of carbon dioxide, hydrogen sulfide, methane, and steam, all the gases blasted out of the rock itself. It's a greenhouse gas blanket, so thick it keeps the planet molten, which is good because it also solves a major riddle. Historians of planetary science still argue over the faint young sun paradox. The puzzle is that our young blue-white sun was actually 30% dimmer than it is today. By all rights, when the Earth finally did cool enough for water to exist, it should have frozen into a solid ball of ice. The fact that it didn't, that it stayed a warm, watery world, is almost entirely thanks to this insane, super-thick greenhouse atmosphere we're seeing right now. But the solar system's construction isn't finished. There are still rogue protoplanets careening around. As you watch the molten Earth spin, impossibly fast, perhaps completing a day in only 5 or 6 hours, you see a new object, a reddish speck in the blackness, growing larger. It's moving too fast. It's not an asteroid. It's on a collision course. This is a protoplanet, the size of Mars, that astronomers have named Theia. It's about to strike the Earth in a glancing blow that will nearly tear our planet apart, and in doing so, will create our nearest companion, the Moon. The mainstream historical fact of this giant impact hypothesis is the single most important event that will happen to our young world, and you're about to have a front row seat. Theia closes the distance over thousands of years, but the final moment is terrifyingly fast. You watch as the Mars-sized planet, a dark red sphere against the black, finally touches the glowing red Earth. This is not an explosion in the way you think of one, with fire and sound. This is a physics event on a scale that strains the imagination. It's a catastrophic merging. Theia strikes the Earth in a glancing blow, and the sheer energy of the impact is almost instantly converted into heat. The entire surface of our planet, which had just begun to form a fragile crust, liquefies in an instant. Theia itself is completely obliterated, its iron core plunging deep into the Earth's own, merging with it. From your perspective in orbit, the event is a silent, slow-motion horror. You see a splash of unimaginable proportions, a plume of vaporized mantle, rock turned into incandescent gas, hotter than the surface of the sun, from both planets is ejected into the void. This superheated plume, containing trillions of tons of molten material, blasts past you and settles into a thick, glowing ring of debris around the shattered Earth. It looks like a miniature, fiery version of Saturn's rings. Down below, the planet is no longer a cherry red. The energy of the impact has heated it to a brilliant, blinding white hot. It's now spinning wildly, wobbling on its axis. This is the mainstream historical fact of the giant impact hypothesis, the event that truly forged the world we know. The immediate aftermath is a scene from a cosmic furnace. The Earth is now spinning so fast from the angled collision that a day might have lasted only 5 or 6 hours. This is a quirky tidbit of astrophysics, but imagine it, a 5-hour cycle of blinding day and molten night. The planet is a perfect sphere of magma, thousands of degrees hotter than before, its atmosphere blasted away and replaced by a temporary new one made of vaporized rock. But your eye is drawn to the new ring. Over the next few years, months, and even days, a stunningly fast process, you watch gravity at work. The glowing debris in the ring begins to collide, to stick, to clump. A few large clumps form first, sweeping up the smaller bits. Then these larger clumps inevitably drift together, their gravity pulling them into a single, massive, coalescing sphere. You are, quite literally, watching the birth of the moon. A new globe of molten rock, smaller than the Earth but still a world in its own right, is born from the wreckage. This new moon is not the pale, distant, comforting disk you know. It is a monster. It's 10 times closer to the Earth than it is today, hanging in the sky so large it fills a huge portion of your view, and it's molten. It glows a dull, angry red, its own surface a sea of magma, heated by its violent formation. This giant, hot, looming presence will dominate the Earth's sky for millions of years, and its incredible gravitational pull will stir the magma oceans of Earth, and later the water oceans, with tides of unimaginable power. This, right here, is the smoking gun. Scientists still argue over the exact timing and composition of Theia, but the scientific evidence is undeniable. When the Apollo astronauts brought back rocks from the moon, they were found to be isotopically identical to rocks from the Earth's mantle. They are made of the same stuff. The moon is, quite literally, a child of Earth, blasted from its own body in this single, defining cataclysm. The Earth is now a sterile, white-hot hell, spinning wildly, with a giant molten companion looming in its sky. The stage is set. The planet is a clean slate, forged in fire, but it's still too hot for, well, for anything. It must cool. And as it cools, the second, even longer reign is about to begin. For hundreds of millions of years, the Earth just cools. It's an agonizingly slow process. The white-hot magma ocean, our home, post-Theia impact, dulls to a glowing red, then finally to a simmering, fragile black. The first crust is born. This isn't a stable continental crust. It's a thin, brittle scab of black basaltic rock, constantly being shattered by the final wave of impacts from the late heavy bombardment. A sort of solar system-wide cleanup crew that pummels the inner planets. But the scab keeps reforming. All this time, that thick, choking atmosphere you saw earlier is still there. A crushing blanket of CO2 and methane. And it is absolutely saturated with water vapor. This is the mainstream historical fact of the late Hadean. All the water delivered by comets and asteroids, plus all the water outgassed from the planet's own minerals as it boiled, is just waiting. It's a global steam bath, waiting for the thermostat to drop. Finally, after perhaps 150 million years of cooling, the surface temperature dips below the boiling point of water, 100 degrees Celsius, 212 degrees Fahrenheit. High in the toxic reddish-brown clouds, a single drop of liquid water condenses. It begins to fall. This isn't a gentle spring shower. You are about to witness the greatest rainstorm of all time. This is a global deluge that will last for, well, scientists still debate the exact timing, but we're talking about a continuous, planet-wide rainstorm that could have lasted for thousands of years. And it's not cold, refreshing rain. It's boiling hot rain, acidic from the carbon dioxide and sulfur in the air, falling from a sky you can't see, onto a crust of equally hot black rock. At first, it just sizzles. You watch the water hit the basalt, instantly flash into steam, and rise right back up into the clouds, only to condense and fall again. It's a planetary-scale pressure cooker, a cycle of steam and sizzle. But slowly, the crust cools enough that the water stays. It begins to pool in the lowest basins, in the vast, shallow craters left by ancient impacts. The deluge continues, a ceaseless, roaring downpour, until the black, rocky surface of the planet disappears beneath a dark, steaming, acidic sea. You are no longer looking at a magma world. You are looking at a water world. This is the Archean eon. Before you lies a global ocean. There are no continents, no land masses as you'd recognize them. The only land consists of thousands of black, jagged volcanic islands, the peaks of a planet-wide underwater crust. They are constantly erupting, spewing sulfur and steam, the planet's inner heat still desperately trying to escape. And you notice immediately, the colors are all wrong. The sky isn't blue. With almost no free oxygen and an atmosphere choked with methane, CO2, and a sulphurous haze, the sky is a sickly, oppressive orange or reddish-brown. The scientific evidence for this comes from geochemical analysis of Archean rocks, which show a complete lack of oxidation. The ocean is even stranger. It's not blue, it's green. This is the great green rust ocean. This is a quirky but vital tidbit of paleogeology. For nearly 2 billion years, the planet's oceans will be saturated with dissolved iron, ferrous iron, which was easily dissolved by the acidic rain from all that exposed volcanic rock. The world is, essentially, covered in a sea of liquid pre-rust. This iron-rich water is a critical piece of the puzzle, and it will later provide the smoking gun for the first great pollution event in history. You're floating above this eerie green ocean, under this oppressive orange sky, watching the black volcanoes hiss. And then you see the tides. Remember that giant, close-up, molten moon? Its gravity is immense. This isn't a gentle lapping of waves. Twice a day, which is still only maybe 10 or 12 hours long, a monstrous tidal wave, a wall of green water perhaps hundreds, even 1,000 feet high, races around the planet. It smashes into the volcanic islands, scouring them clean of any loose rock. In a ceaseless, grinding roar. This is the only sound on Earth, the hiss of volcanoes, the roar of the hot rain, and the thunder of these hyper tides. It's a sterile, violent, alien world. But down in the dark, at the bottom of that green, iron-filled ocean, something is about to happen. The spark is about to be lit. You are now going to leave the raging, noisy surface of the Archean world and sink. You drop below the wind and the monstrous tides, leaving the faint, hazy orange light of the sky behind. You descend for miles, down, down, down into the endless, silent blackness of the green rust ocean. The pressure here is unimaginable, enough to instantly crush any complex life, if any existed. The water is near freezing. This is the abyss, a place that seems totally hostile to life. And yet, in the darkness, you see a glow, not of light, but of heat. As you approach the seafloor, you see a landscape that looks like a fantasy kingdom. Towers of mineral deposits, some 60 feet high, rise from the crust. These are hydrothermal vents. You watch as a plume of superheated, particle-choked water, black with dissolved minerals, billows from the top of a chimney-like structure. This is a black smoker, and the water erupting from it is over 400 degrees Celsius, 750 degrees Fahrenheit, hot enough to melt lead, but it doesn't boil because of the immense pressure. This is where the action is. This is the mainstream historical fact of the chemosynthesis hypothesis. In this total darkness, life cannot use sunlight, so it must use chemistry. These vents are the perfect engine. You have a steep thermal gradient. Boiling hot water from the vent meets freezing cold seawater. And you have a steep chemical gradient. The vent water is rich in hydrogen, methane, and sulfur. The ocean water is rich in CO2. This gradient is energy. It's a battery, a power source, just waiting to be tapped by the first lucky chemical reaction. But how do you get from a chemical soup to a cell? This is the chicken and the egg problem that has puzzled scientists for a century. To build a cell, you need DNA to provide the instructions. But to read the DNA, you need complex machines called proteins, enzymes. But to build those proteins, you need the instructions from the D. So which came first? The scientific evidence now points to a third magical molecule, RNA. This is the RNA world hypothesis. RNA, as you might know, is DNA's less famous cousin. But it has a superpower. It can both store information, like DNA, and act as an enzyme to speed up reactions, like a protein. It's the chicken and the egg, all in one. Now, look closer at the vents. The rock of these chimneys isn't solid. It's a porous, spongy mass of iron-sulfur bubbles, like a mineralized sponge. Each tiny pore, each microscopic bubble, is a natural test tube. Here, the chemical-rich water from the vent is trapped, concentrated. The mineral walls themselves act as catalysts, speeding up reactions. And in these millions of tiny, protected pockets, the RNA molecules are forming. They begin to replicate themselves. They begin to compete. The ones that replicate faster or build a tiny protective wall of fat win. You are not watching a single spark of life. You are watching millions of tiny chemical experiments happening all at once. This is the birthplace of metabolism. This is the birthplace of replication. This is the origin of life itself. From this churning chemical war, the last universal common ancestor, or LUCA, will emerge. Scientists still argue whether LUCA was a single, robust cell or, more likely, a leaky community of these protocells, living in the vent pores and constantly swapping genes back and forth. This idea is far more compelling to many scientists than the classic primordial soup theory. Darwin's warm little pond, where lightning strikes a mix of chemicals. The problem with the soup is that everything just diffuses. It's hard to concentrate the ingredients. The vents, with their mineral-walled pores, solve that problem perfectly. Here's a final quirky tidbit for you, though. What if this didn't happen on Earth at all? This is the panspermia hypothesis. We know that early Mars was also wet and volcanic. What if life started there first, in a Martian hydrothermal vent, and was then blasted into space by an asteroid impact, traveling to Earth as a microbial refugee huddled inside a meteorite? It's entirely possible that the spark wasn't lit here, but was delivered from a neighbor. Life has been sparked in the dark. For the next billion years, a truly staggering length of time, life remains simple, single-celled, and anaerobic. That last part is key. These first bacteria and archaea are poisoned by oxygen. They thrive on sulfur, on methane, on hydrogen, in the dark, in the mud, and in the deep-sea vents where they were born. The world is theirs. But we're going to leave the deep abyss and travel back to the surface, to a shallow, warm, sunlit lagoon on the edge of a black volcanic island. You are now floating in this warm, shallow water, perhaps 3.5 billion years ago. The orange sky is thick with CO2. The sun's hazy light filters down, and you see rocks. Lumpy, cauliflower-shaped, layered mounds looking like living boulders. These are stromatolites. They look like rock, but they are alive. This is a quirky tidbit. These are not a single organism, but a high-rise city of microbes. They are biofilms, layer upon layer of single-celled organisms, bound together with mucus, trapping sediment. And they are still alive today, in a few very salty, protected places like Shark Bay, Australia, giving us a living window into this ancient world. In this microbial city, a new kind of bacterium has evolved. It's called a cyanobacterium, and it has invented a revolutionary new hack to get energy. Up until now, life has been running on the chemical energy from vents or minerals. But there's a much bigger power source available: the sun. These cyanobacteria have figured out how to tap it. This is the mainstream historical fact of the invention of photosynthesis. But this isn't just any photosynthesis. Other bacteria had been doing a simpler version using sunlight and hydrogen sulfide, which produces sulfur as waste. These cyanobacteria invented a new, far more powerful version. They use the energy of the sun to split the water molecule, H2O, to get their hydrogen. The waste product of this new reaction is a molecule called O2, oxygen. From your vantage point, you watch these lumpy green-blue stromatolites sitting peacefully in the green ocean, basking in the hazy sunlight. And you see tiny shimmering bubbles rising from them. It looks peaceful, but it is not. You are witnessing the start of the single greatest pollution event in the history of our planet. This is the Great Oxidation Event, or GOE. Oxygen is not a gentle, life-giving gas. Not to these organisms. To the dominant anaerobic life on Earth, oxygen is a violent poison. It is a highly reactive, corrosive gas that tears apart their cells. You are watching the cyanobacteria, in their ignorance, begin to exterminate almost all other life on Earth. You watch as this poison gas begins to build up in the water around the stromatolites. A war begins. The anaerobic life forms, the original rulers of the planet, are killed off in the surface waters. They are driven into the shadows, deep into the mud, back down to the hydrothermal vents, into any pocket of the world where this toxic new gas cannot reach them. But where does all this oxygen go? For millions, perhaps hundreds of millions of years, it doesn't even reach the atmosphere. It immediately reacts with the first thing it touches. And what is the entire ocean full of? Dissolved iron. That's right. Our green rust ocean is the planet's built-in safety net. You watch one of the most beautiful and terrible processes in geology. As the oxygen bubbles out from the stromatolites, it hits the iron-rich green water and instantly reacts, forming iron oxide. Rust. This rust is solid. It's a particle, and it begins to rain. You watch as a cloud of reddish-brown snow falls from the sunlit upper waters. Gently, ceaselessly, drifting down into the blackness of the deep ocean. This goes on for 1 billion years, an endless, slow-motion rain of rust. This is the scientific evidence, the smoking gun, you can find today. This rust snow settled on the seafloor, creating unimaginably vast layers of iron-rich rock, which were later interspersed with layers of silica. We call them the banded iron formations. They are the source of almost all the high-grade iron ore we mine today to build our cars, our bridges, and our skyscrapers. Every piece of steel in your life is the fossilized remainder of this, the first planetary-scale apocalypse. Scientists still debate whether the GOE was a truly sudden event or a much slower oxidation that took hundreds of millions of years to finally overwhelm the planet's chemical buffers. But either way, the planet is rusting, and eventually the buffer will run out. That endless, slow-motion rain of rust has finally, after hundreds of millions of years, begun to slow. The vast, green, iron-rich oceans have been cleared. The mainstream historical fact is that the planet's great iron buffer is now used up. The dissolved iron is gone, settled onto the seafloor in those massive, banded iron formations that we now mine for steel. But the cyanobacteria in their lumpy, stromatolite cities don't care. They haven't stopped. They are basking in the hazy sun, relentlessly splitting water and pumping out their toxic waste. O2. Now you are at the crisis point. For the first time, this free oxygen has nowhere to go. It can no longer be locked away by iron in the water. So it begins to bubble out of the ocean and leak into the atmosphere, a process that will last for eons. The air above the green-turned clear oceans begins to change, molecule by molecule. And this is where the real catastrophe begins. Remember that hazy, orange, methane-rich sky? Methane is an insanely powerful greenhouse gas, about 80 times more potent at trapping heat in the short term than carbon dioxide. It's been the planet's thermostat, the protective blanket that kept the Earth warm and cozy, even while the sun was 30% dimmer, the faint young sun paradox. But oxygen is a bully. It's a hyperreactive molecule. As it seeps into the air, it immediately attacks the methane, breaking it down, reacting with it, and converting it into two much weaker greenhouse gases: carbon dioxide, CO2, and water vapor, H2O. You are watching, in agonizing slow motion, as the planet's main heating blanket is systematically shredded by this new oxygen poison. The planet's thermostat is now broken. With the methane blanket gone, the Earth can no longer hold on to its heat. The temperature begins to plummet. This is the scientific evidence we see in the geological record. The GOE is immediately followed by the Huronian glaciation, the first and longest ice age in our planet's history. It won't last for a few thousand or even a million years. This deep freeze will grip the planet on and off for 300 million years. From your vantage point in space, you watch it happen. The poles, which had been temperate, begin to frost over. Ice caps form, gleaming white against the clearing ocean. And then they grow. The ice sheets creep down from the poles, year after year, millennium after millennium. The oceans begin to freeze, a crust of white spreading across the globe. You watch as the stromatolites, the very bacterial cities that caused this apocalypse, are entombed in ice. The planet is being flash-frozen, its new life forms smothered by their own success. A scholarly debate rages on about just how bad this got. Was this a true Snowball Earth, a solid ball of ice from the poles to the equator? Or was it, as some models suggest, a slush ball Earth, where a band of open, soupy or thinly iced water managed to survive at the equator, a last refuge for the photosynthetic life that needed the sun? We're not sure, but the quirky tidbit is that the evidence for any of this comes from drop stones, boulders found in ancient marine sediment where they shouldn't be. The only explanation? They were carried out to sea by vast, continent-sized glaciers and then dropped when the icebergs melted. Life clings on. It survives in that equatorial slush, in the thin films of liquid water under the ice, or in the warm, dark oases of the hydrothermal vents. This ice age is a trial by fire, or rather, by ice. It's a brutal filter that will kill off countless lineages. But after 300 million years, the volcanoes, which never stopped erupting under the ice, finally build up enough new CO2 to create a new, weaker greenhouse blanket. The ice melts. The aftermath is a brand new world. The Great Oxidation event has fundamentally changed the planet. The oceans are now clear and blue, stripped of their iron and the sky. The sky is no longer orange. With the methane gone, it is, for the first time, a pale, recognizable blue. This entire global crisis, this 300 million year-long ice age that nearly ended life, was caused by bacteria. It's a terrifying preview of how life, from this moment on, will not just live on the planet, but will actively shape it, driving its climate, its atmosphere, and its very geology. The stage is now set for a new kind of life, one that can use this dangerous new poison, oxygen. The 300 million year-long Huronian ice age has finally broken. The volcanoes, chugging away under the ice, have rebuilt the CO2 in the atmosphere, and the planet has thawed into a new, stable, oxidized world. We now enter a vast new chapter, the Proterozoic Eon. You're floating above a planet that looks more familiar, with blue oceans and a pale blue sky. Below you, the continents have drifted together to form the first true supercontinent that geologists have a good record of, Rodinia. We now enter a period of time lasting from roughly 1.8 billion to 800 million years ago that paleontologists have given a wonderfully uninspiring name, the Boring Billion. And on the surface, they're right. It is a mainstream historical fact that the fossil record seems to just top. The dynamic stromatolites are still there, but they're not really changing. The climate, for the most part, is stable. The geological record is one of slow, steady, quiet sediment. It's as if evolution put on the brakes and the planet took a billion-year nap. But this is perhaps the single greatest misnomer in all of science. The Boring Billion was not boring at all. It was the most revolutionary period in our planet's history since the origin of life. The real action wasn't happening at a macro level. It was a secret, microscopic war that would change the destiny of the planet. Let's dive back into that new blue ocean. The simple cells, the bacteria and the archaea, the prokaryotes, are still the rulers. But there's a new kind of cell in the water. It's huge, 1,000 times larger by volume. It's complex. It has a wall around its genetic material, a nucleus. It has internal scaffolding, a cytoskeleton that lets it change its shape. This is the eukaryote. This is your ancestor. So where did it come from? The scientific evidence points to one of the most bizarre and wonderful events in history: endosymbiosis. It's not a story of slow, gradual change. It's a story of a failed lunch. Here's how it happened. You're watching a larger, more complex Archean cell. It's inefficient. It gets its energy the old-fashioned way, by fermenting scraps in the water. It's also learned a new trick: phagocytosis, the ability to bend its body and swallow other cells. It spots a small, simple bacterium. This bacterium is different. It's a specialist. it has evolved a superpower. It can breathe the toxic oxygen that now fills the seas and use it to produce vast amounts of energy. The big Archean lunges and gulps the small bacterium, swallowing it whole, intending to digest it. But it fails. The small, oxygen-breathing bacterium isn't digested. It survives, trapped inside its predator. And then, a bargain is struck. The host cell, the big Archean, provides a safe, stable home, protecting the bacterium from the outside world and bringing it a steady supply of food, simple molecules. In return, the internal bacterium, living comfortably in its new house, continues to do its oxygen-breathing trick, and it leaks the energy it produces. It leaks so much energy that its host cell is now supercharged, flooded with a surplus of power it's never had before. That internal bacterium is now an organelle. We call it the mitochondrion. This is the quirky tidbit. The power plants in every single one of your cells, the things that let you move, think, and live, are the descendants of this one ancient captured bacterium. The smoking gun? The mitochondrion has its own, separate, bacterial DNA. It reproduces on its own by splitting in two, just like a free-living bacterium. You are a chimera. This is the origin of us. Every animal, every plant, every fungus, every creature you have ever seen that isn't a bacterium is a eukaryote, powered by these ancient captives. And the story didn't stop there. Later, one of these new, supercharged eukaryotic cells performed a second gulp. It swallowed a cyanobacterium. That cyanobacterium also survived, becoming the chloroplast, the internal solar power capturing engine. This was the birth of the plant lineage and all algae. So scientists still debate the exact timing of this, but the boring billion was the era of this secret war. It was the invention of the hunter cell, the phagocyte, and the hunted, leading to this incredible symbiotic truce. It wasn't boring. It was the quiet, hidden arms race that built the complex cellular machinery that would eventually be ready to build the first animal. The boring billion had to end, and it ends with a cataclysmic breakup. The giant supercontinent Rodinia, which had been a stable, single landmass for hundreds of millions of years, begins to rip itself apart. You watch from space as huge tectonic plates crack, rift valleys form, and new, smaller continents begin to drift away from each other. This breakup is the mainstream historical fact that triggers the most dramatic climate change in our planet's 4.6 billion-year history. But why does a continental breakup cause an ice age? It's a bit of a paradox, but it's all about rain. As Rodinia breaks up, you create thousands of miles of new coastline. You create new, jagged mountain ranges as the continents collide and crunch. This new topography drastically changes weather patterns, leading to a huge increase in global rainfall. Here's the trigger. Rain is nature's great air scrubber. As raindrops fall, they dissolve atmospheric CO2, forming a weak carbonic acid. This acid rain then falls on all that newly exposed fresh rock along the coasts and on the new mountains. The acid reacts with the rock, chemically locking the CO2 away as carbonate minerals like limestone, which then wash into the sea. You are watching the planet suck its own greenhouse blanket out of the atmosphere. The thermostat breaks again, just like it did in the Huronian, but this time it's on a monstrous scale. The CO2 levels in the atmosphere plummet. The planet begins to cool. Ice caps form at the poles. And now, the albedo effect takes over. Albedo is just a measure of reflectiveness. White ice is highly reflective. As the ice caps grow, They reflect more sunlight back into space, which makes the planet colder, which allows more ice to form, which reflects even more sunlight. It's a runaway positive feedback loop. A climate death spiral. This is the cryogenian period, and you are about to witness Snowball Earth. From your vantage point in space, you watch the white ice caps creep down from the poles year after year. They spread, covering the land, and then they start to cover the oceans. The white of the ice merges at the equator. The planet is white. It's a gleaming, perfect cosmic cue ball. The entire Earth, from the poles to the tropics, is encased in a shell of ice perhaps a mile thick. The average temperature is -50 degrees Celsius. This is the scene, a silent, white, frozen world, glittering in the faint light of the sun. Scientists still argue over this in what's known as the hard snowball versus slush ball debate. Did the Earth freeze completely solid, a hard, impenetrable ball of ice? Or was it a slush ball, where a thin, soupy, barely liquid band of open water and broken ice managed to cling on at the equator, a last refuge for life? How do we even know this happened? The scientific evidence is one of the most brilliant pieces of geological detective work ever done. Geologists found drop stones. These are large, out-of-place boulders found sitting in the middle of extremely fine, deep ocean marine sediments. There is no force in the deep ocean that can move a boulder. The only explanation is that the boulder was frozen into a glacier. The glacier floated out to sea as an iceberg, and as it melted, it dropped its stony cargo into the mud below. That's fine for the poles, but here's the kicker. We find these drop stones in rocks that, based on their magnetic signature, were located at the equator. We find glacial deposits in the tropics. The ice was global. So, did life die? No. Life is tenacious. But it was driven to the absolute brink. Where did it hide? 1. Hydrothermal vents. The planet's inner fire was still on. The deep-sea vents, in their total darkness, didn't even know there was an ice age. They just kept pumping out heat and chemicals, a dark, warm cradle. 2. Under the ice. In the deep ocean, the sheer pressure and the faint warmth from the Earth's core may have kept a thin film of liquid water at the bottom of the ice sheet. 3. The quirky tidbit. On the surface of the ice, in cryoconite holes. These are tiny, self-contained ecosystems. A speck of dark dust or grit lands on the ice, absorbs sunlight, and melts a small pocket of water. In this tiny sunlit pool, algae and bacteria, our new eukaryotes, could form a miniature self-sustaining world. This 100-million-year-long crisis, this snowball, was a pressure cooker. It was an evolutionary filter of unimaginable intensity. It was forcing those new, complex eukaryotic cells to adapt or die. They were trapped in these tiny refuges, these cryoconite holes, these dark vents, for millions of years. And the pressure was forcing them to find a new survival strategy: cooperation. Huddling together to share resources, to protect each other. This intense global filter is the leading hypothesis for what finally pushed these cells to take the next great leap: to invent multicellularity. The first animals were being forged in this ice. How does a snowball Earth ever end? It seems like a permanent, stable state. The white, reflective ice should keep the planet frozen forever. But you have to remember the planet's inner fire. All through those 100 million years of ice, the volcanoes never stopped. They kept erupting under the ice, under the mile-thick glaciers, pumping out CO2 and other greenhouse gases. Here's the key. With the entire ocean frozen over and no rain falling, there was no mechanism to scrub that CO2 out of the air. For millions of years, the CO2 from volcanoes just built up. It accumulated in the atmosphere, above the ice, getting thicker and thicker until it reached insane concentrations, perhaps 350 times higher than today's levels. This is the mainstream historical fact of the thaw. Eventually, this colossal greenhouse blanket became so thick that it overpowered the albedo effect, the ice's reflectivity. The planet's thermostat, which had been stuck on cold, was suddenly jammed to hot. You are about to witness the hothouse rebound. The ice begins to melt, and it doesn't melt slowly, over millennia. Scientists still debate the exact timing, but the transition may have been catastrophically fast, perhaps taking only a few thousand years. You watch as the mile-thick ice sheets collapse, crack, and melt, unleashing the single greatest flood in Earth's history. The oceans, which had been trapped, are now flooded with trillions of tons of fresh water. But that's not all. As the glaciers melted, they dumped all the rock they had been grinding up for millions of years into the sea. The oceans, which had been clear and sterile, are now choked with nutrients, phosphorus, iron, and other minerals. And what loves a warm, shallow, nutrient-rich, sunlit sea? Algae. The eukaryotic algae that had survived in those tiny slush ball refuges now go insane. You are watching the single largest algae bloom in world history. The entire ocean, globally, turns green with life. And what do all these algae do? They photosynthesize. They pump out massive amounts of oxygen. This is the second great oxygenation event, a huge pulse of O2 that will bring the atmosphere's oxygen levels up to something approaching modern levels. This sets the stage for big animals. The snowball is gone. The hothouse has cooled. The air is breathable. The world is ready. You dive into this new ocean in the Ediacaran period, around 600 million years ago. You are expecting to see, well, something. Fish? Trilobites? But the seafloor is covered in... What are these things? This is the Ediacaran biota, the first true large-scale multicellular life on Earth. But they are weird. They look like evolution's first failed draft. You see Dickinsonia, a flat, quilted, pancake-like creature, some a few feet across, lying on the seafloor. You see Charnia, which looks exactly like a fern or a sea pen, a frond-like organism, but the fossils show it lived miles deep, in total darkness, where photosynthesis is impossible. You see Kimberella, a slug-like thing that seems to be moving, scraping the microbial mats for food. This is a quirky tidbit that baffles scientists. These things are alien. They seem to have no mouths, no guts, no anuses, no obvious predators. They don't seem to be animals or plants or fungi. The leading theory: they are a completely separate kingdom of life that has since gone extinct. They may have simply absorbed nutrients directly from the water through their flat, quilted bodies, like giant, living mats. They are a lost kingdom. They are the first experiment. They are the weirdos. They prove that after 4 billion years, the world is finally ready for big life. But this entire bizarre quilted kingdom is not our ancestor. They are a dead end. They will all vanish, making way for a new, second experiment in complex life, an explosion that will include our ancestors. The Ediacaran weirdos have vanished. They were a beautiful, strange, quilted failure. The stage is now cleared, and the next great era, the Paleozoic, is dawning. But the next great leap, the first true conquest, won't happen in the sea. The animal explosion is still waiting in the wings. Before that, the plants are about to make their move. We're going to leave the ocean and stand on the shore of a vast continent. You are on the first land on Earth, and it is utterly, profoundly alien. Look around. There are no trees, no grass, no flowers, no soil. There is nothing but an endless, sterile expanse of grey, sun-baked rock and gravel. The sun above you is a harsh, unfiltered, violet-white glare. The ozone layer, which will one day protect us from UV radiation, is still thin and patchy. The mainstream historical fact of this era is that the land is a desert, a dead zone. What do you smell? There is no outdoors smell. There is no damp earth, no pine, no pollen. The air smells of dust, of the sharp, metallic tang of sun-baked rock, and the faint, acrid whiff of sulfur from a distant volcano. What do you hear? The silence is absolute. It's a dead, empty world. The silence broken only by the hiss of the wind scouring the gravel and the distant, lonely crash of waves on the shore. But right at your feet, in the splash zone where the tide meets the rock, something is happening. Green algae, eukaryotes that have been thriving in the shallow coastal waters for 1 billion years, are clinging to the rocks. For millions of years, they've been getting splashed, then drying out, then getting splashed again. They've been slowly evolving a tolerance for this harsh new world. But they can't do it alone. The rock is food poor. They can't get the minerals they need to survive. So, they make a deal. This is the quirky and absolutely critical tidbit. They form a symbiotic odd couple with fungi. Fungi are master decomposers. They are the planet's chemists. They have an incredible superpower. They can eat rock. They excrete powerful acids that dissolve the rock, etching it and liberating the precious minerals, the phosphorus, the iron trapped within. You are watching the birth of the first lichen. It's a perfect partnership. The fungus dissolves the rock, providing a steady supply of minerals and a tough, protective house that holds on to water. In return, the algae, safe inside, does its photosynthesis trick and provides a steady supply of sugar. You watch as a greenish-gray, scabby crust appears on the rocks at the water's edge. This is the first pioneering life on land. This lichen is the foothold scientists still debate whether the first ever land plant was a lichen, a pure alga, or a simple moss. But the scientific evidence from the oldest fossil spores strongly suggests this ancient, rock-eating fungal partnership. From this partnership, the next step evolves. The first true, simple plants. The bryophytes. You would call them mosses. You see a patch of them. They are a revolution. They have no true roots, no leaves, no wood. They are just a simple stem and a leafling. But they can hold water in their tiny structures. They can survive. You watch as this thin, bright green fuzz begins to creep, millimeter by millimeter, inland from the coasts, following the rivers and streams. This green creep is the Ordovician revolution. This is the first greening of the continents. These humble mosses and their fungal partners are doing something no one has ever done before. They are making soil. They are breaking down the rock. And when they die, their bodies create the first layer of organic humus. They are building the foundation for every forest and field that will ever exist. They are heroes. But as you watch this green fuzz conquer the grey rock, you can't know that these humble mosses are too successful. Just like the cyanobacteria before them, they are about to change the world's climate so drastically that they will trigger the planet's first great mass extinction. We return to the ocean, 541 million years ago. The strange, quilted, passive world of the Ediacaran weirdos is gone. You are now a witness to the Cambrian explosion. This is the mainstream historical fact of the Paleozoic era. But the name is a bit misleading. It wasn't a poof, like a stick of dynamite. It was an explosion, in the way a flower explodes in slow motion. It was a sudden geological event, taking place over perhaps 20 million years, in which almost every single major animal body plan, what we call a phylum, appears in the fossil record. Before this, life was simple. It was microbes, algae, and weird quilted mats. After this, the oceans are suddenly, shockingly, filled with animals. Animals with heads, tails, legs, guts, and eyes. You are seeing the birth of the modern animal kingdom. So, why now? Why, after 4 billion years of quiet, did life suddenly get so complex and violent? Scientists still argue over the exact trigger, but it seems to be a perfect storm of 3 things. 1. The oxygen trigger. Remember that massive algae bloom after the Snowball Earth? It pumped the oceans and atmosphere full of oxygen. You can't be a big, active, hunting animal without a high-octane fuel, and oxygen is that fuel. The environment was finally ready for high-energy lifestyles. 2. The genetic trigger. Deep in the eukaryotic cell, a new set of master genes had finally evolved. We call them Hox genes. You can think of them as the genetic toolkit for building a complex body. They are the master instructions that tell an embryo. Put the head here, put the legs here. Make this part a segment. Life had finally invented the code to build complex creatures. 3. The ecological trigger. This is the most exciting one. The invention of predation. The simple passive Ediacaran world of just being was over. An animal, somewhere, evolved the first rudimentary mouth and the first rudimentary gut. It figured out how to eat its neighbor. This was the shot that started the race. You are floating over the new Cambrian seafloor, and you can see the scientific evidence of this new, terrifying, eat-or-be-eaten world everywhere. The seafloor is no longer covered in soft mats. It's covered in armor. Geologists call this the small shelly fauna. It's a layer of rock littered with millions of tiny mineralized bits, spines, shields, cones, and simple cap-like shells. This is the invention of biomineralization. Life has learned to pull minerals, calcium carbonate, calcium phosphate, out of the seawater and build hard parts. This is a revolution on par with the invention of the wheel. A shell is armor. It's your first line of defense against being eaten, but it's also the first skeleton. It provides a rigid structure for muscles to attach to, allowing for leverage, power, and speed. This is the invention of offense and defense. The ocean floor is now teeming. It's no longer silent. You can hear the scuttling, clicking and scraping of thousands of tiny armored bodies, and your eye is drawn to the new king of this world, the absolute icon of the Cambrian, the trilobite. You see them everywhere. They are arthropods, the ancestors of insects, spiders, and crabs. They look like a cross between a horseshoe crab and a giant woodlouse. They have a segmented body, a hard, mineralized exoskeleton, their armor, and dozens of jointed legs. But their most shocking feature: they have eyes, big, complex, compound eyes, the first sophisticated visual organs on the planet. They can see you. They are the cockroaches of the Cambrian, wildly successful, diversifying into over 20,000 known species. Some are scavengers, snuffling through the mud. Some are filter feeders, and some are hunters, using their new eyes to find their prey. And here's the quirky tidbit about those eyes, the ultimate proof of their advanced, mineralized nature. Unlike your soft, protein-based eyes, a trilobite's eyes were made of rock. Their lenses were made of pure, crystalline calcite, the same mineral that forms limestone. They literally had crystal eyes, a unique optical system, perfectly preserved in the fossil record, that allowed them to see their world with a sharp, digital clarity. The arms race had begun. But as successful as the trilobites are, they are just the normal ones. To really understand the Cambrian, you have to see the experiments we're now traveling to a specific spot. A shallow reef in what will one day be the Canadian Rocky Mountains. This is the Burgess Shale. This fossil bed, a mainstream historical fact, is a perfect snapshot, a Lagerstätte, where the soft bodies of the era's strangest creatures were preserved in exquisite detail. You are floating in a warm, sunlit sea, and you are no longer in an ecosystem. You are in evolution's sketchbook, looking at the first, wild, often failed drafts of animal life. Look over there. What is that? It's about 3 inches long, swimming awkwardly. It has 5 eyes on stalks, bobbing around, looking in all directions at once. And from the front of its head, it has a long, flexible, hose-like appendage, like a vacuum cleaner's nozzle, and at the very end of that nozzle is a claw. You watch as it uses this bizarre proboscis to grab a small worm from the mud and curl it back toward a mouth that is under its head and facing backward. That is Opabinia. It is so strange that when the scientist who first described it presented his reconstruction at a conference, the entire room burst into laughter, thinking it was a joke. It gets weirder. Look down at the seafloor. There's a small, wormy creature crawling along. It appears to be walking on stilts. This is Hallucigenia. It's a tiny creature, maybe an inch long, with 7 pairs of sharp, needle-like spines, like stilts, that it walks on. On its back, it has a row of 7 feathery tentacles that it presumably used to filter food from the water. This is the quirky tidbit of Cambrian paleontology. For decades, scientists got this creature completely wrong. They reconstructed it upside down, thinking it walked on the soft tentacles and used the hard, sharp spines for defense. They also couldn't tell its head from its tail. It was so confusing that they named it for the hallucinatory nature of its body. Next to it is Waiwasia. It looks like a futuristic, armored slug. It's a soft, slug-like creature on the bottom, but its entire back and sides are covered in what look like overlapping, scale-like plates of armor, and from its back protrude 2 full rows of enormous, carbon fiber-like spines, some as long as the creature is wide. It's a defensive nightmare. You can hear the constant, gentle chittering and scraping of all these new, hard-shelled creatures moving over the rocks. The water is warm and, for the first time, full of sound. But in the middle of all this strangeness, a small, flat, worm-like creature, about 2 inches long, ribbons past you. It looks boring. It has no armor, no spines, no 5-eyed stalks. That is Pikaia. It is perhaps the most important animal in this entire sea. Because if you look closely, you can see it has a stiff, flexible rod running down its back. That is a notochord. It's the scientific evidence of the first primitive backbone. This boring little worm is a chordate. It is your great-great-great-great-great-uncle. While evolution was busy designing spike-covered slugs and 5-eyed nozzle monsters, it was also, almost quietly, designing us. So why? Why so weird? The Burgess Shale is the ultimate proof that the Cambrian explosion was a time of frantic, unbridled experimentation. Evolution was throwing every possible body plan at the wall to see what would stick. Before it settled on the body plans that would survive, arthropods, mollusks, chordates, it produced this Cambrian weird world. Scientists still argue over what these things even are. Were Opabinia and Hallucigenia just failed branches of existing phyla, like weird experimental arthropods and worms? Or were they members of entirely new phyla, whole categories of animal life that were born, lived for a few million years, and then vanished completely, leaving no descendants at all? It seems that in the Cambrian, building an animal was a new art, and you are looking at the entire bizarre, beautiful, and terrifying first gallery. This arms race, this new, violent world of spikes and crystal eyes, needs a boss. All this new defense must be a reaction to a new kind of offense. You are floating over a vast, sunlit bed of trilobites, watching them scuttle and graze. Suddenly, a shadow falls over the seafloor. It's not a small shadow. It's big. You look up, and you see the Leviathan of the Cambrian. It's 3 feet long. In a world where most creatures are the size of your thumb, this makes it a monster. This is Anomalocaris, the abnormal shrimp. This is the mainstream historical fact of the Cambrian. It was the world's first large apex predator. Its body is sleek and flexible, with wings on its sides that it undulates to fly through the water with terrifying speed and agility. Its head is a nightmare of specialized weapons. On the front, it has 2 huge, complex eyes on stalks, giving it stereoscopic vision. These are some of the largest and most complex eyes of the era, more than capable of spotting a trilobite in the mud. Below its eyes, it has 2 long-jointed, grasping appendages, bristling with sharp, backward-facing spikes, perfect for snatching and holding slippery prey. And then, its mouth. It doesn't have a jaw. It has a nightmare. It's a circular, squarish ring of overlapping, razor-sharp plates that looks like a cheese grater or a pineapple slice. You are about to see it hunt. It spots a large trilobite scuttling for cover. In a burst of speed, Anomalocaris darts down. The 2 spiked appendages snap forward, caging the trilobite. The trilobite, with its advanced calcite crystal eyes, saw it coming and has rolled into a defensive ball, but it's too late. The Anomalocaris pulls the balled-up trilobite toward its terrifying, grinding mouth. You hear a crunch, a sickening sound of shell shattering, as the predator's mouthplates crush the exoskeleton to get at the soft body inside. This isn't speculation. The scientific evidence for this is direct and chilling. Paleontologists have found numerous fossilized trilobites from this period with distinctive W-shaped bite marks and crush injuries on their shells. These wounds are a perfect match for the bizarre, square-ringed mouth parts of Anomalocaris. This was a hunter so effective, it literally left its signature on its victims for 500 million years. Now here's the quirky tidbit that shows just how baffling this alien world was to the first scientists who discovered it. For decades, Anomalocaris wasn't known to exist. It was misidentified as 3 different animals. 1. Its grasping, spiky arms were found alone and named Anomalocaris. Abnormal shrimp, because that's what they looked like. 2. Its circular cheese-grater mouth was found alone and named Peytoia, believed to be a jellyfish. 3. Its main, soft body was found alone, without the arms or mouth, and was classified as a sea cucumber. It took decades for paleontologists, staring at these shrimp, jellyfish, and sea cucumbers all found in the same rock, to have the aha moment. They realized they were all parts of one single giant monster. They finally pieced the puzzle together and realized they were looking at the Cambrian's T-Rex. This complex, vibrant, violent world seems like it could last forever. The Burgess Shale, weird wonders, are experimenting. The trilobites are thriving, and the abnormal shrimp is ruling the seas. But the planet is a fickle stage. The party is about to end. The Cambrian period, which began with an explosion, ends with a whimper. We see the Cambrian Ordovician extinction event. This isn't one of the big 5 mass extinctions, but it's a serious pulse extinction. The cause is still debated, perhaps a sudden change in sea level or a rapid anoxic event where the oxygen suddenly disappeared from the water, suffocating the new high-energy life forms. It's a reset. Most of the weird wonders, the opabinias and hallucigenias, are wiped out completely. Evolution's sketchbook is slammed shut. The trilobites are decimated, with many of their most successful families vanishing forever. The world is being cleared again, making way for the survivors to radiate and build a new, even more complex world in the next chapter. The Ordovician. The Cambrian Ordovician extinction has done its work. The weird wonders of the Burgess Shale are gone, and the world has been reset. We now enter the Ordovician period. This isn't an explosion of new, bizarre ideas like the Cambrian. This is something more profound. It's the Great Ordovician Biodiversification Event, or GOBIE, a mainstream historical fact where life doubled and then tripled its diversity. This is the moment when the survivors of the Cambrian, the phyla that worked, began to fill out all the empty ecological niches. This is the construction of the first truly complex, modern-style marine ecosystems. You are floating in this new Ordovician sea, and it is teeming. It's crowded. The most stunning new feature. The first true coral reefs have appeared, but they aren't made of the corals we know today. These are ancient, extinct tabulate and rugose corals, and they are building massive, complex, 3-dimensional cities in the shallow tropical seas. These reefs are bustling with new players. The seafloor is no longer just trilobite territory. It's covered in brachiopods, which look like clams, but are a totally different phylum with a different shell structure. Vast, dense gardens of crinoids, or sea lilies, have taken root. They look like feathery, delicate flowers. But they are animals, related to starfish, filtering the water with their fern-like arms. And the trilobites that survived the extinction? They are back, diversifying into new, strange forms. But the real innovation is happening with our own distant family, the chordates. Swimming awkwardly just above the seafloor are the first fish you see one. It's underwhelming. It looks like a small, muddy tadpole, maybe a foot long, but it's completely encased in heavy, bony armor. This is an ostracoderm, or shell-skinned fish. This is our ancestor, the first true vertebrate. But it's a defensive creature. It has no jaw. Its mouth is just a simple, round, sucking hole. It's a mudsucker, hoovering up detritus from the sea floor. The quirky tidbit about these ostracoderms is that they invented bone. Not as an internal skeleton, that would come later, but as external armor. They are essentially living, swimming shields, a desperate defense against the real rulers of this new ocean. Anomalocaris is gone. Its reign as the apex predator is over. Now a new, even more terrifying shadow falls over the reef. You look up, and you see something that defies logic. It looks like a 30-foot-long telephone pole swimming horizontally. This is Cambrian. It is a straight-shelled nautiloid, an ancient relative of the modern squid and octopus. But instead of a coiled, compact shell, its shell is an enormous, straight, pointed cone. From the wide, open end of this 30-foot-long shell, a squid-like head emerges, with huge, intelligent, staring eyes, a forest of grasping tentacles, and a sharp, parrot-like beak hidden in the center. This is the new apex predator. This is the scientific evidence we see in the fossil record. These giant conical shells are found all over the world, and it moves like a monster. It hunts via jet propulsion. You watch as it sucks a huge volume of water into its body cavity and then fires it out a siphon, propelling itself backward with a sudden, powerful thump. Its prey? The eurypterids, the sea scorpions, which have also just appeared. These are giant, armored arthropods, some 6 feet long, with pinching claws. They are vicious predators in their own right, but they are no match for the Cambrian. You watch the hunt. The giant nautiloid spots a eurypterid in the reef. It takes aim, its huge eyes calculating the distance. Thump! It jets backward, closing the gap in an instant. The tentacles explode outward, a writhing cage that envelops the sea scorpion. You hear a sharp, sickening clack as its powerful beak snaps shut, punching straight through the eurypterid's armor. Scientists still debate exactly what these giants hunted: sea scorpions, trilobites, or even the new armored fish. But they were, without a doubt, the undisputed 30-foot-long kings of the Ordovician. You are floating in the late Ordovician, and the world is in a perfect, stable rhythm. The great reefs you saw are thriving, teeming with crinoids, brachiopods, and the new armored, jawless fish. The giant Cambrian rules the deep, and on the continents, the first great greening is a wild success. That humble green fuzz, the partnership of moss and fungi, has conquered the coastlines and river valleys, creating the first soil and the first smell of damp earth. It is a paradise. But you know the rule by now. Life is its own worst enemy. Those humble, heroic mosses are too successful. They are, right now, triggering the planet's first great mass extinction. This is the Ordovician Silurian extinction, the first of the Big Five. And scientists are still debating the finer points, but the leading hypothesis places the blame squarely on plants. Here's the kill mechanism, a two-part crime. 1. CO2. Drawdown. Just like the cyanobacteria before them, the mosses are voracious. They are photosynthesizing, sucking trillions of tons of CO2 out of the atmosphere to build their tiny bodies. 2. Rock weathering. This is the real killer. Remember their fungal partners? They are dissolving the rock, etching the continents with their acids to get minerals. This chemical reaction, acid on rock, also pulls CO2 from the air, locking it away as carbonate. You are watching these tiny, innocent-looking plants strip the planet's greenhouse blanket away. The thermostat, which had been set to paradise, is now plummeting toward icebox. From your vantage point in space, you watch a new ice cap form, this time over the massive southern supercontinent, Gondwana. This is the mainstream historical fact of the event. A monstrous glacier, miles thick, begins to spread, covering an area larger than modern-day Africa. This kicks off the kill mechanism, and it's a brutal 1-2 punch that we can read clearly in the scientific evidence of the rock layers. Punch 1. The Ice Age begins. As this massive amount of water is pulled from the oceans to build the glacier, sea levels plummet. You watch as the water level drops by hundreds of feet. All those beautiful shallow water tropical reefs? They are now high and dry. They are exposed to the air and the sun, and the entire complex ecosystem, the corals, the crinoids, the brachiopods, dies. It's a global habitat catastrophe. This lasts for 500,000 years. Then a brief interglacial period. The planet warms slightly, the ice melts, and the sea levels rise again, flooding the now dead reefs. The few species that survived, the ones that could handle the cold, deep water, begin to spread out, thinking the worst is over. Punch 2. The planet snaps back into an even deeper freeze. A second pulse of glaciation, even more severe than the first, hits the world. The sea levels plummet again. This second, more rapid punch is the quirky tidbit of this extinction. It's what makes it so deadly. It kills off the cold water survivors who had just begun to recover. It's a gotcha move by the climate, a double tap that ensures almost nothing can adapt. The toll is unimaginable. You watch as the seas, once crowded, become quiet and empty. This is not a small event. This is the second deadliest extinction in the history of the world. 85% of all marine species are wiped from the face of the Earth. The great Cambrian, the 30-foot apex predator, is gone. Vanished. The trilobites are decimated, their 270-million-year story nearly ending right here. The beautiful reef ecosystems are shattered. And the cause of it all? The irony is gut-wrenching. The humble moss, the life on land, survives just fine. It was, in its evolutionary infancy, completely oblivious to the fact that it had just nearly murdered all life in the oceans. The world is reset. The slate is wiped clean. Again. The ice has melted. The Ordovician Silurian extinction, the great plantocalypse, is over. We have now entered the Silurian period. The planet has thawed, the sea levels have risen, and the survivors of that 1-2 punch are inheriting a new, recovering, and radically different ocean. The survivors are in a world with a power vacuum. The mighty Cambrian, the 30-foot jet-propelled torpedo, is gone. The apex predator niche is wide open, and the survivors that rush in to fill it are the Eurypterids, the sea scorpions. You are in a shallow, warm Silurian sea. You see a shadow move over the seafloor. It's a pterygotus. This is a sea scorpion, an arthropod, a relative of spiders and, well, scorpions, and it is the size of a crocodile. It's 8 feet long, a flattened, terrifying swimming tank. It has paddle-like hind legs to propel it through the water, and at the front it has 2 enormous spiked, pinching claws that it holds out in front of it. These are the new kings. They are the mainstream historical fact of the Silurian. They are the top predators, and you watch as one snaps its claws, effortlessly grabbing one of the few surviving trilobite species. But this reign of claws is about to be challenged by a revolutionary new invention. It's happening in a very unlikely, humble group, our own ancestors, the vertebrates. Remember those armored, jawless, mud-sucking ostracoderms? They were defensive. They were prey. They survived the extinction, and now one group of them is about to change the world. They are about to invent the jaw. This is, without a doubt, one of the most profound evolutionary hacks in the history of life. And here's the brilliant part. Jaws are not new bones. Life didn't invent them from scratch. It repurposed what it already had. Here's how it worked. All these primitive fish have a series of gill arches, C-shaped bars of cartilage or bone that hold their gills open so they can breathe. You're watching this evolutionary process in slow motion. The first gill arch, the one closest to the mouth, begins to migrate forward. It becomes stronger, hinged in the middle, and it bends. The top half moves forward to become the upper jaw. The bottom half moves forward to become the lower jaw. That's it. A piece of breathing scaffolding becomes a weapon. The implication of this one simple tweak is absolute. It changes the face of the planet. Vertebrates are no longer just passive mud suckers or filter feeders. They can bite. They can grasp, crush, shear, and defend. This is the moment your ancestors stop being just food and start fighting back. You see the first terrifying results of this invention. The placoderms, the plated skin fish. They are still covered in that heavy, bony armor. But now, they have jaws. You see one swim by. It doesn't have teeth yet. Instead, its actual jawbones have been honed into self-sharpening, razor-sharp, bony blades. It's a swimming guillotine! And here's the quirky tidbit that connects you directly to this moment. For a long time, scientists still debated whether any of these early fish were our ancestors. Maybe they were all weird side branches. Then, in China, they found a fossil called Entomognathus. It was a placoderm, but it had a complex jaw. In fact, it's the first animal ever found to have the exact same set of jawbones that you have. A dentary, your lower jaw, a maxilla, and a premaxilla, your upper jaw. This 420-million-year-old armored fish is your great-great-great-uncle, and you are staring at the first face in history that you would actually recognize as a face. This is the Great Split. The jawed fish, the Gnathostums, are born. They immediately radiate into 2 other major lines. 1. The acanthodians, or spiny sharks. They look like sharks, but they're covered in bony armor and spines. 2. The chondrichthyes, the true cartilaginous sharks, and the osteichthy, the bony fish. That last group, the bony fish, is the one that will one day lead to us. The invention of the jaw has just lit the fuse on the age of fishes, and in the far, far distance, the entire age of tetrapods. The sea scorpions just became obsolete, and they don't even know it yet. The Silurian period is in full swing. The oceans are a brutal, high-stakes game of eat or be eaten, ruled by 8-foot-long sea scorpions and the new, terrifying jawed placoderms. But we're going to leave that aquatic war zone and go back to the land. You're standing on the shore, and it's no longer the empty grey rock world from the Ordovician. It's green. That humble moss and fungi partnership has been busy. The coastlines and riverbanks are covered in a thick, damp, springy carpet of green. It's a new, untouched continent of food and territory. And the animals, trapped in the predator-filled ocean, are finally starting to notice. But why leave the water? It's been life's home for 4 billion years. Scientists still argue over the exact prime mover for this great invasion, but it was likely a push and a pull. 1. The push, predator evasion. The ocean is terrifying. It's full of giant claw-wielding monsters. The land, it has nothing. No predators. It's safe, it's boring. And right now, boring is a great way to stay alive. 2. The pull, new food source. That green, mossy carpet is an all-you-can-eat buffet, an untapped resource. And, more importantly, tiny mites and springtails have already made the journey and are happily munching on that moss. It's a brand new food chain, just waiting for a consumer. 3. The quirky tidbit. A fringe theory. Maybe they just came ashore for sex. That's not a joke. Laying your soft, defenseless eggs in a sea full of armor-crushing monsters is a terrible strategy. But scuttling ashore and laying your eggs in the damp, protected, safe moss, that's a brilliant way to ensure your offspring survive. So, who makes the great leap first? It's not our vertebrate ancestors. It's not the fish. It's the arthropods, the creatures with their skeletons on the outside, the ancestors of insects, spiders, and millipedes. This is the mainstream historical fact of the land invasion, and they were perfectly pre-adapted for it. They had 2 huge advantages. First, they already had an exoskeleton. That waxy, jointed shell is not just for protection. It's waterproof. It's a natural spacesuit that keeps their insides from drying out. A fish out of water is a dead, dried-out husk in an hour. An arthropod is just annoyed. Second, they already had jointed legs. A fish has to invent limbs from fins. An arthropod already has legs. It just has to learn to use them to support its own weight against gravity, rather than just scuttle along the seafloor. But there was one massive, seemingly impossible hurdle. Breathing. Their gills are beautiful, feathery structures designed to pull tiny amounts of dissolved oxygen from water. In the open air, they would instantly collapse, dry out, and the creature would suffocate in minutes. The solution is a masterpiece of evolutionary hacking. You're watching an early scorpion-like creature. Over millions of years, its gills have been modified. They've been internalized, pulled deep inside the body to stay safe and wet. And they've been folded over and over into a stack of thin, damp, leaf-like layers. Like the pages of a book, this is the invention of the book lung. It's a brilliant way to maximize surface area for gas exchange while keeping the whole delicate structure protected and damp. It can pull oxygen straight from the air. We know they made it. The scientific evidence is undeniable, etched in stone. In Scotland, we have found the oldest fossil trackways of any land animal. They are the tiny, scuttling, multi-legged footprints of a creature called Pneumodesmus, an early millipede. These little tracks, left in damp Silurian mud, 428 million years ago, are the one small step for animal life on land. You're standing on a Silurian beach. The air smells of low tide, rotting algae, and that new, rich, damp earth smell from the moss. You watch as a creature that looks like a cross between a spider and a scorpion, a trigonotarbid, one of the first arachnids, crawls slowly out of the surf. It's hesitant. It stops, sensing the new, strange, dry air with its antennae. It makes a desperate, scuttling run across the wet sand, making for the safety and, crucially, the dampness of the green, mossy bank where it vanishes. It's a momentous occasion. Life is no longer just in the sea. It is on the land. The invasion has begun. We now move into the Devonian period. The oceans are in an arms race, rightly earning this era the nickname the Age of Fishes, which we'll get to. But the most profound changes are still happening on land. That green, mossy carpet was just the beginning. It was Act 1. You are now about to witness Act 2, the invention of height. You're standing in a damp, lowland basin. The mosses are still here, but they are being overshadowed by a bizarre new flora. The first thing you see is a creature called Cooksonia. It's not impressive. It's just a simple, green, branching stick, maybe a few inches tall. It has no leaves. It has no roots. It just has a little spore cap at the tip of its branches. But this humble little plant is a revolution. This is the mainstream historical fact of the Devonian. Cooksonia is the first vascular plant. What does that mean? It has invented an internal plumbing system. If you looked inside, you'd see specialized cells called tracheids and a tough new polymer called lignin. This is the invention of wood. This simple, rigid pipe system does two things. 1. It can suck water up from the ground, defying gravity. 2. It provides structural support, allowing the plant to stand up straight and get tall, reaching for the most valuable resource of all, sunlight. This is the start of the war for the sky. But before true trees take over, the landscape is dominated by one of the most bizarre, quirky tidbits in the entire history of life: prototaxites. You are walking through this landscape of knee-high Cooksonia and mosses. But looming over you, like silent, pale towers, are pillars. They are 20, even 30 feet tall. They are grayish-white. They have no leaves, no branches. They are just spires. They look like the world's largest, most terrifying mushrooms. And here's the thing. They were. For decades, scientists argued over what prototaxites was. The scientific evidence was baffling. Was it a rolled-up mat of algae? A bizarre giant lichen? A monster? In 2007, a chemical analysis of the fossils finally solved the mystery. The carbon isotopes showed, definitively, that this thing was not a plant. It was a heterotroph. It ate other things. It was, in fact, a colossal 30-foot-tall fungus. For 20 million years, before true trees evolved, the tallest living things on Earth were giant mushroom spires. They were the kings of this alien landscape, likely eating all the dead moss and plant litter, the planet's first giant decomposers. But their reign is short-lived. The invention of wood is too powerful. The vascular plants are in their own arms race. You watch as evolution invents two more crucial pieces of technology. 1. Roots. True, deep-digging roots to anchor the plant and suck up more water. 2. Leaves. Broad, flat, green solar panels to capture more light. By the late Devonian, the giant mushroom trees are gone. They have been overshadowed and replaced by the first true forest on Earth. You are standing in a grove of Archaeopteris. These are true trees, 70 feet tall, with massive root systems and branches covered in delicate, fern-like leaves. This is the scientific evidence we see in the Gilboa Forest fossil site in New York. This changes everything. For the first time, there is such a thing as shade. The forest floor is dark, damp, and cool. The air, for the first time, is still. The wind is broken by the canopy. And the sound. You hear the wind whistling through the first true leaves, a sound that has never been heard on this planet before. You can smell it. The sensory experience is overwhelming. It's the rich, deep, complex smell of damp earth, of rotting wood. The fungi have finally caught up, and the sweet, green smell of a living forest. Life has created a brand new three-dimensional world on top of the old flat one. But as you stand in this beautiful, revolutionary new forest, you can't know the terrible secret. Those new, powerful roots, they are about to trigger the next mass extinction. While those revolutionary new forests are busy conquering the land and creating the smell of rot, we're heading back to the ocean. Because in the Devonian period, the land is not the only place having a revolution. The seas are in the grip of an arms race so total, so dominated by one type of creature, that this entire 60-million-year-long era is famously known as the Age of Fishes. The invention of the jaw has proven to be the single most disruptive technology in the history of the ocean. The old, jawless, armored ostracoderms are being hunted to extinction. The seas are now ruled by the plecoderms, those plated skin fish who were the first to turn their jawbones into razor-sharp blades. And in the 70 million years since they first appeared, they have evolved from small, guillotine-faced guppies into monsters. You are floating in the warm, open water of a Devonian sea. The water is a bit murky, filled with the new plankton that has evolved. A school of small, early sharks. Yes, sharks have now appeared, but they are not the bosses. They are small, 3-foot-long prey, darts past you. They are fleeing from something. You feel a deep, powerful thump in the water, a pressure wave that you feel in your chest. And then you see it. It's not a fish. It's a nightmare. It is Dunkleosteus. This is the mainstream historical fact of the Devonian. This is the king. It is 30 feet long, the size of a large great white shark, but built like a tank. Its entire head and shoulders, a massive 6-foot-long section of its body, is encased in thick, interlocking, bony armor plates. It looks less like an animal and more like a submarine designed by a medieval executioner. It is, without question, the apex predator of this world. You drift closer, and you look at its mouth. This is the quirky tidbit. Dunkleosteus has no teeth. It doesn't need them. It has done something far more terrifying. Its actual jawbones, the massive, bony plates of its skull, have grown into self-sharpening guillotine-like blades. The upper tooth is a giant, bony fang. The lower jaw is a massive, sharpened blade that, when the mouth closes, slots inside the upper fang, constantly grinding against it, sharpening itself with every single bite. It is a living, 30-foot-long pair of bone shears. And the bite. The scientific evidence on this is terrifying. Biomechanical models based on its huge, powerful muscles, which we can reconstruct from the fossils of its armored skull, show it had one of the most powerful bites in the history of life. But it wasn't just strong, it was fast. Scientists still debate the exact speed, but it's believed Dunkleosteus could open its massive, bone-blade jaws in as little as 1/50th of a second. This did two things. First, it created a vacuum, a suction force so powerful it would inhale any prey, like those small sharks, that got too close. Second, the snap of the jaw closing was one of the fastest and most powerful in history, shearing through anything. We have the proof. We find the fossils of its prey, other armored fish and sharks, that have been bitten cleanly in half, not nibbled, not torn apart. Guillotined. You are about to see it. That school of 3-foot Cladocelarch, the early sharks, zips by. The Dunkleosteus drifts, its armored head like a turret. It targets one. It doesn't chase in a long pursuit. It strikes. It opens its mouth, a click thump so fast it's just a blur, and the vacuum sucks the shark in. The snap of the bone blades closing is a horrifying, dull crack that echoes through the water. The shark, armor, cartilage, and all, is sliced in two. The Dunkleosteus swallows the back half and lets the front drift, unconcerned. This is the king. This is the top of the food chain. The oceans are a complex, thriving world of sharks, nautiloids, and the last of the giant sea scorpions. And this 10-ton armor-plated guillotine rules them all. It seems invincible, but as you watch this monster patrol its kingdom, you are unaware that a crisis is brewing. A new mass extinction is about to begin. And the killer? It's not a new predator. It's not an asteroid. It's those beautiful revolutionary new Archaeopteris trees, the ones that are right here. Brand new invention, deep, powerful roots into the soil for the first time. The land is about to murder the sea again. You are standing in that beautiful, revolutionary Archaeopteris forest. It's the world's first forest, a 3-dimensional, shaded, complex world that has fundamentally changed the land, but it's also a murderer. Those trees are about to kill the ocean. We are now in the late Devonian, and you are about to witness the second great mass extinction caused by plants. This is the late Devonian extinction, another one of the Big 5 mass extinctions. This is the mainstream historical fact of this era, a devastating crisis that will reshape the planet. And the killer? It's not an asteroid. It's dirt. Here is the kill mechanism. Remember that the Archaeopteris tree invented 2 new pieces of technology: leaves and, crucially, deep, powerful roots. For the first time, plants are not just clinging to the rock. They are pulverizing it. You can almost hear it. The roots are digging deep, cracking the rock, releasing minerals. The falling leaves are creating a thick, acidic layer of humus, rot, on the surface to us. You are witnessing the birth of massive amounts of soil. This is a quirky but vital tidbit. For the first 4 billion years of Earth's history, soil as you know it, that rich, black, organic-filled dirt, did not exist. It was an invention of the Devonian forest. And this new invention is the murder weapon. You watch as rain falls on these new, dense forests. It's not a gentle rain on bare rock. It's a deluge that churns this new, loose, nutrient-rich soil and mud, carrying it away in torrents. Rivers that once ran clear are now thick, brown, and soupy, choked with phosphorus, nitrogen, and all the other minerals that the roots and rot have liberated from the land. This brown, soupy mud flows into the oceans. From space, you watch a horrifying sight. The oceans near the coasts, especially in the vast, shallow inland seas, begin to turn green. Not the clear iron green of the Archean, but a thick, putrid, soupy green. This is a eutrophication event, the single largest algal bloom in the history of the world. All those algae, supercharged by this sudden, insane buffet of nutrients from the land, explode in population. They cover the surface of the water in a thick, slimy mat, blocking the sun. The complex ecosystems below, the reefs, the trilobites, begin to starve of light. But the real killer is what happens when all this algae dies. The bloom is so massive, it can't sustain itself. Trillions of tons of dead algae sink from the surface, down into the water column, down to the sea floor. And now the bacteria wake up. A population explosion of decomposing bacteria begins to eat this rain of dead algae. And just like you, these bacteria breathe. They use oxygen to do their work. In a matter of decades, this bacterial bloom sucks all the dissolved oxygen out of the water. This is the anoxic event. The oceans suffocate. The scientific evidence for this is undeniable. All over the world, geologists find a thick, black layer of rock from this exact period. It's black shale. It's black because it's full of dead, organic matter, the algae, that never rotted, because there was no oxygen to rot it. It just settled, along with the suffocated bodies of the ocean's animals, into a black, toxic dead zone mud. You are back in the water, floating over a reef. But it's silent. The water is a dark, stinking, toxic soup. The toll is unimaginable. 75% of all species on Earth are wiped out. The placoderms, the armored guillotine fish, are hit the hardest. The king, the mighty, 30-foot, armor-plated Dunkleosteus, is gone. It did not die in a glorious battle. It choked to death in its own toxic, suffocating sea. The trilobites take another massive hit, their 270-million-year dynasty barely clinging on by a thread. The great reefs are gone. The ocean is, once again, empty. Scientists still debate whether this was one long, slow-burn extinction or, more likely, a series of smaller, rapid pulses of anoxia, like a killer striking the planet over and over for 20 million years. But life finds a way. Who survived this new oxygen-poor world? 1. The sharks, who were smaller, more adaptable, and perhaps lived in different, deeper or cleaner open ocean waters. 2. The bony fish, a group that had split into two crucial lineages. The ray-finned fish, who will go on to become 99% of all fish today, and the lobe-finned fish. And this is the final crucial consequence. This anoxic, suffocating, poisoned water creates an intense, desperate evolutionary pressure for any animal living in the shallow, choked river deltas and swamps. The water has no oxygen. You cannot breathe in it. The pressure is on. You must find another way to get air. You must breathe the atmosphere. The survivors of this great plantocalypse are now being forced by the dead hand of the forest to look up, out of the water, to the air. The age of fishes has been choked to death, and the age of the land fish is about to be born. You are now in a very different place. You've left the dead, deep, anoxic oceans, and traveled to a river delta, a shallow, muddy, freshwater swamp at the very end of the Devonian. The world's first forests line the banks, their roots and leaves choking this water with so much rotting organic gunk that it's a thick, brown, oxygenless soup. This swamp is a death trap for any animal that relies on gills, and yet it's full of fish. How? Because this is where the survivors, the bony fish, are staging their next great evolutionary leap. You see one surface, it's a fish, but it gulps the air. This is a lobe-finned fish, a group that includes modern-day lungfish. And it has a superpower. Its swim bladder, the little gas bag that other fish use for buoyancy, has been rewired. It's connected to its esophagus, and it's rich with blood vessels. It's a primitive lung. This fish can breathe air. But it has another even more important trick. Look at its fins. They're not the thin, papery, fan-like fins of a goldfish. They are fleshy. They are muscular. They are lobed. And if you X-rayed one, you'd see a quirky but vital tidbit that changes the course of history. Inside that fleshy fin is a single, thick, upper arm bone, a humerus, followed by two lower arm bones, a radius and ulna, followed by a cluster of wrist bones. This is the scientific evidence. This is the exact one-too-many bone pattern that is in your arm right now. You are no longer looking at a fin. You are looking at a proto-limb. You see one of these fish in the shallows. It's a panderichthys, a fishapod, as paleontologists call it. It looks like a fish, but it has a flat, crocodile-like head with its eyes on top, not on the side. It's propping itself up on the muddy bottom with those new, muscular, arm-like fins, its head just above the surface, breathing the air. But then you see the star of the show, the ultimate missing link, discovered in 2004 by a team led by Dr. Neil Shubin. This is Tiktaalik. It's a 3-foot-long creature that is a perfect 50-50 split between fish and land animal. It has scales and gills and fins. But it has a flat head with eyes on top. It has a neck. It's the first fish in history that can turn its head, scanning the bank, independent of its body. It has massive, reinforced ribs, like a land animal, to support its body against gravity. And its fins. They are fins, yes, but they are more. It has shoulders. It has elbows. It has wrists. It can bend its fin at a 90-degree angle. You watch as it does something no fish has ever done before. It lifts its body, pushing its chest off the mud in the world's first push-up. You watch its behavior, and you suddenly understand why this is happening. The water is a stinking anoxic soup. The Tiktaalik is miserable. It uses its powerful front fin limbs to drag itself, to haul its body out of the suffocating water up onto a muddy bank or a fallen log. It collapses on the mud, gulping the rich, life-giving air into its new, primitive lungs. This is the key. This is the mainstream historical fact. The invasion of the land was not an ambitious conquest. It wasn't a fish deciding to go for a walk. It was a desperate escape. It was a fish fleeing the aquatic apocalypse that the plants had caused. The lungs came first. The limbs came second. They weren't walking legs, they were hauling out of the water arms. Scientists still debate this very point. Were these new, powerful limbs first used for walking on the bottom of the swamp like a modern mud skipper? Or were they immediately co-opted for this new, life-saving trick of hauling out onto the land? The evidence from Tiktaalik, with its powerful shoulders and reinforced ribs, strongly suggests the hauling hypothesis. It was an animal in transition, an amphibian in waiting, a refugee from its own suffocating sea, and it has just, by accident, taken the first real step toward conquering the continents. The world of Tiktaalik was a world of desperate escape. That fisherpod, with its push-up-ready arms and air-gulping lungs, was a refugee, not a conqueror. But in the millions of years that follow, in those choked, muddy swamps, its descendants take that desperate act and turn it into a lifestyle. You are now witnessing the birth of the first true tetrapods, the four-limbed animals. The dynasty that includes you. We are at the very, very end of the Devonian. The forests are now mature. The air is thick, humid, and rich with oxygen, though not as rich as it will become. You are crouching on a mud bank, at the edge of one of these brown, soupy swamps. You hear a sound, a wet, heavy slapping, and then gasping, a strange, gulping, hiccuping sound. A creature hauls itself out of the water. It's one of the Adam and Eve generation of land vertebrates. This is Ichthyostega. It is not a graceful creature. It is not a proud conqueror. It is ugly. It looks like a 3-foot-long, very muscular, very depressed salamander, but it's still covered in tiny fish-like scales, and it has a fishy tail fin running down its back. Its head is broad and flat, like Tiktaalik's, with those same eyes on top for peering out of the water. Its legs are short, stout, and sprawled out to the side, like a modern crocodile's. It moves with agonizing effort. It plants its front limbs, locks its massive, overlapping ribs, which form a rigid, barrel-like cage to support its organs against gravity, and then it drags its back half forward. Slap, gulp, drag. This is not walking. This is hauling. And look at its feet. This is the quirky tidbit that proves evolution was still just making things up. Ichthyostega doesn't have 5 toes. It has 7. Its cousin, Acanthostega, who was even more aquatic, had 8. You are looking at a moment in time before the 5-fingered hand had become the standard. Evolution was still experimenting, throwing numbers at the problem, trying to figure out the best way to build a foot. The 5-fingered pentadactyl limb that you have wasn't an inevitability. It was just the one version that happened to survive. So, what is this creature doing on land? For a long time, we pictured Ichthyostega as the great pioneer, confidently striding from pond to pond. But the latest scientific evidence paints a very different and much stranger picture. Scientists still debate just how terrestrial this creature was. The Ichthyostega fossil has a very telling clue. Its ear. Its ear bones are structured in a way that is perfectly adapted for hearing underwater. An air-based ear like yours is built differently. Furthermore, Acanthostega's limbs were so front-heavy, and its wrists so inflexible, it's very unlikely it could have walked on land at all. Its arms and legs were probably used as paddles, or for navigating the tangled, log-choked shallows of the swamp. So this isn't a land animal. You are looking at an aquatic animal that, just like its ancestor Tiktaalik, could merely visit the land. It was a swamp monster, a fish that had evolved limbs to better navigate the land-water interface. It came ashore not to explore, but probably just to bask in the sun, like a modern crocodile, to warm its body, or to escape a predator in the water. But it is tethered to that swamp by an invisible, unbreakable leash. This is the mainstream historical fact that will define the next 40 million years. This is the great problem that Ichthyostega and its descendants, the first amphibians, cannot solve: reproduction. You watch as the female Ichthyostega drags her heavy body back into the shallows. She lays her eggs, and you see them, shimmering in the brown water. They are soft. They are gelatinous. They are a jelly. They look just like the eggs of a modern Uday frog or salamander. This is the jelly egg, the amniotic egg. It has no shell. It has no waterproof covering. If she were to lay these eggs on that dry mud bank, they would desiccate and die in an hour. This is the leash. This is the tyranny of the water. No matter how good their lungs get, no matter how strong their legs become, they must return to the water to breed. They are slaves to the swamp. They may be the first to visit the continents, but they will never, ever conquer them. To do that, one of their descendants will have to invent a spaceship, a private pond. They will have to invent the egg. The Devonian is over. Its anoxic oceans and swamp-bound pioneers giving way to a new, strange, and supercharged world. We have now entered the Carboniferous period, an era that will last for 60 million years. And the first thing you notice is the trees. The first experimental forests of the Devonian are gone. They have been replaced by a single, planet-spanning biome. You are standing in the middle of a vast, global, tropical swamp. It's a coal swamp, and it stretches from horizon to horizon. But these are not trees you would recognize. You look up, and your eye is drawn to the kings of this forest. Lepidodendron, the scale tree. It's a colossal 100-foot-tall, 6-foot-wide behemoth, but it's not a tree in the modern sense. It's a club moss, a distant, monstrously overgrown relative of those tiny ground-creeping plants you might see in a modern forest. Its trunk is a strange greenish-gray, covered in a diamond-shaped pattern of scales, the leaf scars left behind as it grew. It doesn't have branches at the top, just a crown that forks over and over into a tangle of smaller stems covered in grass-like leaves. Next to them are the calamites, giant 60-foot-tall horsetails, looking like monstrous jointed bamboo canes. And the understory? It's a dense 30-foot-tall jungle of giant ferns. This is a world of spores, not seeds, a world of green, damp, alien botany. The sensory experience is overwhelming. The air is thick. It's incredibly humid, damp, and hot. A permanent steamy mist hangs between the scale tree trunks. And the smell. The air doesn't smell fresh. It smells of decay, of damp, of mold, and rot. It's the rich, musty, overpowering smell of a swamp that covers an entire planet. But here is the quirky and absolutely critical tidbit of this entire era. Look down. The floor of the forest is a graveyard. It's littered with the fallen trunks of giant lepidodendron trees, some piled 10 feet deep, but they aren't rotting. This is the secret of the Carboniferous. These new trees have invented lignin, the tough woody polymer that lets them stand tall. But the bacteria and, crucially, the fungi that can decompose lignin have not evolved yet. Wood, this new supermaterial, is indestructible. So when a 100-foot-tall scale tree dies and falls over, it just sits there. And another one falls on it, and another. You are walking on a 50-foot-thick mat of unrotted dead trees, going back millennia. This is the mainstream historical fact of the era. This vast planetary layer of dead wood gets covered by mud in the swamps. It gets buried, and over millions of years the heat and pressure cooks it. It becomes coal. Every lump of coal we burn today, the stuff that fueled the Industrial Revolution, is just the mummified, unrotted bodies of these specific Carboniferous scale trees. But this creates a second, even more profound consequence. Photosynthesis, as you know, pulls CO2 from the air. When a tree rots, that CO2 is released right back into the atmosphere by the decomposing fungi. But here, there is no rot. All that carbon pulled from the air to build the tree is just getting buried. It's being taken out of the system. But the oxygen, O2, the waste product of photosynthesis, is not being buried. It's being pumped into the air, and staying there. The scientific evidence, which we find trapped in ancient air bubbles in amber, is shocking. For this 60 million year period, the atmosphere is not the 21% oxygen you are breathing now, it's 35% oxygen. You are breathing an atmosphere that is hyper-oxygenated. The air is thick, almost syrupy, with this rich, high-octane fuel. This has two world-changing implications. 1. Easy energy. For any animal breathing with primitive lungs, this is a bonanza. It's like strapping a supercharger to a lawnmower engine. You get way more bang for your buck with every single breath. 2. Fire. This is the terrifying part. At 35% oxygen, the air is insanely flammable. A spark from a lightning strike wouldn't just start a fire. It would create an explosion. Even wet, green wood, which is almost impossible to light today, would catch fire and burn with ease. This world is a tinderbox, constantly being ravaged by apocalyptic, fast-moving wildfires. You are standing in a hot, damp, misty, alien swamp, breathing a thick, explosive supergas, walking on a 50-foot thick carpet of mummified trees that will one day be coal. This is the Age of Giants, and this supercharged atmosphere is about to create monsters. This atmosphere, this 35% oxygen-rich air, isn't just a fire hazard. It's a life support system on overdrive. And it has a dramatic, logic-defying effect on the animals that have already conquered the land, the arthropods. Remember, arthropods like insects, spiders, and millipedes don't have our efficient balloon-like lungs. They breathe using a much simpler, more passive system. Insects and millipedes use a network of tiny silver tubes called trachea that just pipe oxygen directly from the air to their tissues. Spiders and scorpions use those book lungs, which are also just passive, damp surfaces. This system is terribly inefficient. It only works if oxygen can diffuse down those tubes, and that diffusion only works over very short distances. This is the mainstream historical fact that acts as a physical speed limit on insect size today. The 21% oxygen in our air just can't get deep enough, fast enough, to power a big body. A house spider is small for a reason. But here, in the Carboniferous, with the air supercharged to 35% oxygen, that speed limit is gone. The diffusion is so efficient, so rich, that it can easily saturate a huge body. You are in a world where the physical constraints on arthropod size have been lifted, and the results are the stuff of pure, undiluted nightmares. You're pushing your way through the giant 30-foot-tall, damp ferns. You hear a sound, not a footstep. It's a sound like tank treads, a rhythmic, heavy clacking and scraping sound. You freeze. Out of the mist, a creature emerges, pushing aside the giant fern fronds like they're grass. It is Arthropleura. You are looking at a millipede that is 8.5 feet long and 3 feet wide. It is the size of a small car, or a very large sofa. Its body is a series of 30-odd, broad, armored plates, gleaming in the misty light. From its sides ripple hundreds of tiny legs, clacking on the carpet of unrotted leaf litter. It is, without question, the largest land-dwelling arthropod of all time. It rears up slightly as it encounters a fallen log, its small head waving, its 2 complex antennae tasting the air. You are justifiably terrified. This is a monster. But here is the quirky tidbit. It's probably not here to eat you. For a long time, scientists assumed this nightmare tank must have been a vicious predator. But then they found the scientific evidence. Fossilized gut contents and coprolites, which is the polite scientific term for fossilized poop, belonging to Arthropleura. And what was inside? Not bones, not crushed-up amphibians. It was spores, billions of them, from the giant ferns and scale trees. You were looking at a carcad-boised, armored, herbivorous millipede, which in all honesty is almost weirder than it being a predator. The air is so thick with oxygen, you can almost feel the buzz of it. And then you hear it. A literal buzz. Not the high-pitched, annoying zzzt of a modern mosquito or dragonfly. This is a deep, throbbing, whirring sound, like a small drone or a model airplane. A shadow passes over you. You look up. Flying over the swamp is Meganeura. It's a dragonfly, or more accurately a griffinfly, with a 2.5-foot wingspan. That is the size of a modern hawk or a crow. It's a shimmering, iridescent aerial predator, its huge compound eyes, each with thousands of lenses, scanning the air. Its prey? The other giant flying insects, like the Paleodictyoptera, which were like giant, beaked proto-cockroaches. You watch this hawk-sized dragonfly tackle another insect mid-air, a flash of wings and a loud, sharp clack of its mandibles that you can hear from the ground. The gigantism is everywhere. You look down, near a rotting log, one that's finally being broken down by early fungi, and you see a scorpion. But it's not a small, desert dweller. It's Pulmonoscorpius, the breathing scorpion. It is 3 feet long. It's a walking armored tank-like arachnid, its tail and stinger held high, its claws snapping. This, of course, raises a question for which scientists still argue. Was it just the oxygen? The high oxygen allowed for the gigantism, but it may not have been the driver. The driver may have been a classic evolutionary arms race. In a world with no flying vertebrate predators, birds and bats are 200 million years in the future, the sky was the limit. For insects, they got big just because nothing could stop them. The oxygen was just the fuel that made it possible. And what about our ancestors, the tetrapods, the descendants of Ichthyostega? They are thriving here. This hot, humid, swampy world is paradise for them. They are still amphibians, still tied to the water to lay their jelly eggs. So a planet-sized swamp is the best thing that ever happened to them. And they, too, are huge. You hear a splash in the dark, swampy water. You see a long, flat, crocodile-like snout emerge. But it's not a crocodile. This is Proterogyrinus, a 10-foot-long amphibian. It's a semi-aquatic predator, a swamp monster that hunts the giant fish in the water, and maybe even the giant insects that get too close to the water's edge. This is the Carboniferous world. It's a lost kingdom of giants. a planet-spanning, flammable swamp fueled by an explosive, oxygen-rich atmosphere and populated by car-sized millipedes, hawk-sized dragonflies, and 10-foot-long salamanders. It's a world built on a floor of mummified, unrotted trees, a world that seems like it will last forever. But it's all about to come crashing down. You are standing in the heart of the great Carboniferous coal swamp, a world of giants. 10-foot amphibians lurk in the dark water. Hawk-sized dragonflies own the thick, misty air. It is a world in perfect balance, a paradise for any creature that loves the water. And that is exactly the problem. The tetrapods, our ancestors, have reached a major fork in the road. One group, the amphibians, has doubled down on this swampy lifestyle. They are the masters of the land-water interface. Creatures like Proterogyrinus are perfectly adapted to hunting in the water and basking on the mud banks. 2. But another group is quietly emerging, living in the shadows of the giant scale trees. These are the reptiliomorphs, the reptile-shaped animals. They are small, lizard-like, and they are different. They are trying to solve the one great, unsolved problem of the tetrapod dynasty: the tyranny of the jelly egg. As long as you have to lay your soft, gelatinous eggs in the water, you can never leave the water. You are a slave to the swamp. If that swamp ever dries up, you are doomed. But one of these small reptiliomorphs has evolved an invention, a piece of biological technology so profound it will change the course of evolution and one day lead directly to you. It is the amniotic egg. You are crouching on the damp, peaty forest floor, far from the water's edge. You watch a small, lizard-like creature, something like Hylonomus, one of the first true amniotes, find a safe spot among the rotting but not rotting logs, and she lays her eggs. Right here, on the dry land. This is a revolutionary act. It's the equivalent of an astronaut stepping onto the moon. Look at the egg. It's not a soft, jelly-like orb. It has a tough, leathery, semi-permeable shell. This is the mainstream historical fact of the Carboniferous. This shell is the wall of a biological spaceship. It keeps water in, preventing the embryo from drying out, but it's porous enough to let oxygen in and CO2 out. But the real magic is inside. This is the scientific evidence we see from studying modern reptiles, birds, and, yes, mammal embryos. The amniotic egg isn't just a shell, it's a complete, self-contained private pond. Inside, the embryo floats in a fluid-filled sac called the amnion. This is its private pond, its life support system, protecting it and keeping it wet. It has a lunchbox, a yolk sac, that feeds it. It has a waste storage tank called the allantois, a sac that collects the embryo's toxic waste so it doesn't poison itself. And it has a lung, the chorion, a membrane that presses against the inside of the shell, handling the breathing. This is the invention that cuts the cord. This is the spaceship that allows vertebrates to leave the ocean behind forever. The amphibians are tethered to the water. The new amniotes are liberated. They can now turn their backs on the swamp and march inland to conquer the vast, dry, empty continents. And here is the terrifying coincidence. This revolutionary new piece of technology, the Get Out of the Swamp Free card, evolves at the exact geological instant that the swamp itself is about to be destroyed. The 60-million-year-long party is over. You feel a chill in the air. The thick, humid mist begins to thin. The climate is changing. We are entering the Carboniferous rainforest collapse. The cause is debated. Scientists still argue whether it was a natural climate cycle or, in a bit of quirky irony, if the plants themselves caused it by burying so much carbon, the coal, that they finally crashed, the planet's greenhouse effect. Either way, the planet enters a new, sharp ice age, the Karoo Ice Age. It's not a Snowball Earth, but it is a global cooling and, most importantly, a drying. The effect is catastrophic. The planet-sized swamp cannot survive in a cold, dry world. It dies. You watch as the great lepidodendron scale trees go extinct. The vast global forest fragments. It shatters into 1,000 tiny, isolated islands of swamp, separated by vast, dry, open plains. This is an apocalypse for the giants. 1. The giant amphibians are doomed. Their paradise, their planet-sized pond, is gone. They are trapped in these shrinking islands of wetness, and one by one, they go extinct. 2. The giant arthropods are double doomed. First, their swampy habitat is gone. Second, and more importantly, the oxygen levels plummet. With the coal engine of the forests turned off, the 35% oxygen atmosphere crashes back down to something much closer to modern levels. The Carcendarthropleura and the hawk-sized Meganeura suffocate. Their inefficient, passive breathing systems fail. The age of giants is over. It ends not with a bang, but with a gasp in a cold, dry world. Who survives this apocalypse? The small amphibians, the ones who can survive in the last, tiny remaining ponds and lakes. And us, the amniotes, the small, adaptable, lizard-like creatures who don't need the swamp. They look at this new, dry, cold, empty world not as a catastrophe, but as an invitation. The planet has just been handed to the only creatures that have a spaceship to explore it. The reign of the reptiles and their strange synapsid cousins is about to begin. The Carboniferous rainforest collapse was a global apocalypse. The giant insects have suffocated. The giant amphibians have vanished. The 60-million-year-long age of giants is over, and the planet is, once again, reset. We now enter the Permian period, the final dramatic chapter of the entire Paleozoic era. You are standing on a planet that has been fundamentally re-engineered. You look at a map of the Earth, and you no longer see separate continents and vast oceans. For the first time in hundreds of millions of years, all the major continental plates, Gondwana, Laurasia, and the rest, have collided. They have crunched together in a slow-motion, planet-wide tectonic pile-up, forming one single, colossal landmass. This is the supercontinent Pangaea. This is the mainstream historical fact of the Permian. This has a profound effect on the climate. The world is no longer a globe of humid, swampy coastlines. The interior of this new supercontinent is now thousands of miles from the nearest ocean. You are standing in this interior, and it is a desert. It's a vast, dry, harsh, continental climate of scorching hot summers and bitterly cold winters. This is a hard world. And who is built to survive this new, dry, hard world? Not the amphibians, who are still pathetically enslaved to their last few remaining ponds. No, this world belongs to the amniotes, the creatures who invented the spaceship egg. With that one invention, they look at this endless dry desert not as a barrier, but as a highway. These amniotes, the heroes who survived the collapse, have now split into two great dynasties. Two families that will battle for control of the planet for the next 200 million years. And this is the quirky but vital tidbit. The entire split is defined by a simple piece of plumbing in the skull. It's all about holes! You can look at the skull of any amniote and see which family it belongs to. 1. Sauropsids. This group has one or zero fenestra, or hole, in the skull behind the eye. This is the reptile line. This dynasty will eventually produce lizards, snakes, crocodiles, and, in the far distant future, dinosaurs. 2. Synapsids. This group is different. It has two distinct holes in the skull behind the eye. These holes allow for bigger, stronger, more complex jaw muscles. This is a line. This dynasty will eventually produce mammals. And now, here is the single most important, most misunderstood fact of this entire era. This is not the age of reptiles. The dinosaurs are still 100 million years in the future. The sauropsid reptile line, in the Permian, consists of small, lizard-like, marginal creatures. The Permian is the age of synapsids. Our side of the family won. Our ancestors, the mammal-like reptiles, a bad, old-fashioned term, ruled the world. You are standing on a dry Permian plain, and you are about to meet the king. You see it. It is 15 feet long, weighs 500 pounds, and it is the first true megafauna on land. It has 4 powerful, sprawling legs, a huge, deep, dinosaur-like head full of sharp, differentiated teeth, incisors, canines, a synapsid specialty. And on its back is its iconic, unbelievable sail. This is Dimetrodon! And let's get this straight, right now. Dimetrodon is not a dinosaur. It is a synapsid. That 15-foot-long, sail-backed, terrifying monster is more closely related to you than it is to a T-Rex. It is on our branch of the family tree. The sail, of course, its most famous feature. A series of impossibly long, skin-covered spines sticking straight up from its vertebrae. What on earth was this for? Scientists still argue over its primary function. Was it for display? A giant, flashy billboard to attract mates or intimidate rivals, like a modern peacock's tail? This is a very strong possibility. Or was it for thermoregulation? This is the classic theory, and the scientific evidence is compelling. Dimetrodon was cold-blooded, living in a harsh, desert-like world with cold nights and hot days. In the cold morning, it could turn its sail broadside to the faint, rising sun. It was a giant solar panel. Models show that this massive surface area would have allowed it to warm up its body and its muscles from a cold night stupor to hunting ready in a fraction of the time it would take its prey, like the sauropsid Edaphosaurus, which had a different kind of sail. You are watching this 500-pound synapsid, our cousin, patrol its territory. It is the undisputed apex predator of the early Permian. It is the king of a world ruled by our family. The reign of the synapsids has begun, and it seems like nothing can possibly go wrong. The reign of Dimetrodon, the sail-backed king of the early Permian, eventually comes to an end. The climate of Pangaea continues to shift, and like all dynasties, the first line of rulers gives way to the next. But this is not a defeat for our family. It's an upgrade. The Synapsid dynasty, our dynasty, continues to rule. But the new rulers are a far more advanced, far more mammal-like group called the Synapsids. You are looking at one now, and the difference is profound. This is the mainstream historical fact of the mid-Permian. The new Synapsids no longer sprawl Dimetrodon walked with its legs splayed out to the side, like a modern lizard. These new creatures have their legs tucked directly under their bodies. This parasagittal stance is a revolutionary invention. It's the stance of a dog, a horse, or a human. It's mechanically vastly more efficient, allowing for stamina, speed, and long-distance travel, a crucial advantage in the vast, dry deserts of Pangaea. And there's more. Scientists still debate exactly when true, stable, warm-bloodedness, endothermy, evolved. But the scientific evidence in the bones of these Synapsids points right here. When we slice their fossils, we see Haversian canals, a complex, dense, mammalian-style bone structure that indicates fast growth and a high metabolism. A cold-blooded reptile grows slowly, in fits and starts. These creatures grew fast, like a modern mammal. To do that, you must have a high-octane internal furnace. You must be warm-blooded. This means the creature you're looking at, this proto-mammal, is probably covered in fur to insulate its warm body. It probably has whiskers, vibrissae, to feel its way in the dark. You are no longer looking at a lizard-like creature. You are looking at a wolf-like one. And at the top of this new, warm-blooded, fast-moving food chain is the apex predator, the Gorgonopsian. You see one now, stalking through the dry plains. This is Inostrancevia. It is 11 feet long, sleek, and powerful. It's a terrifying, beautiful chimera, a cross between a saber-toothed cat, a wolf, and a giant monitor lizard. It moves with a new, fluid, mammalian gait, its body held high off the ground. But its head is the weapon. It has a huge canine, a 6-inch-long, dagger-like saber tooth. This is the first true saber-toothed predator on Earth, a predator that evolved this specialization 200 million years before the famous Smilodon. These teeth aren't for chewing, they are for stabbing and shearing. But what do you hunt with 6-inch-long sabers? You need prey with thick hides. You watch as the Inostrancevia stalks its prey. 1. Scutosaurus. This is a sauropsid, a member of the reptile line. It's a 10-foot-long walking tank. It's slow, bulky, and its entire body is covered in thick, bony armor plates called osteoderms, with bony knobs on its head. It's a tough, well-defended plant-eater. The Gorgonopsian is fast, powerful, and built Toby pass that armor, delivering a single devastating saber-toothed bite to the soft throat. 2. Moschops. This is another Synapsid, one of our cousins. It's a bizarre, 16-foot-long, hippo-sized herbivore. Its most notable feature is its insanely thick skull, several inches of solid, dense bone. Scientific evidence, like impact scars on the fossils, suggests they head-butted each other with incredible force, like modern bighorn sheep in battles for dominance. The ecosystem is complex, advanced, and utterly dominated by our Synapsid line. But it's not all monsters and tanks. Here is the quirky tidbit. You see one of the strangest, most comical creatures of the era, Cotylohynchus. This is another Synapsid herbivore, but it looks like a biological joke. It has a massive, 11-foot-long, barrel-shaped body, and the tiniest, most ridiculously small head you have ever seen on a creature that size. It looks like a walking 1,000-pound fermenting tank with a walnut on top. That giant barrel-shaped body wasn't fat. It was a giant fermentation vat, an enormous, complex gut needed to digest the incredibly tough, fibrous, dry land plants of Pangaea. This is the peak. This is the Permian world. It's a stable, complex ecosystem. The Synapsids, our family, have conquered every major niche. We are the top predators, Gorgonopsians. We are the giant, head-butting herbivores, Moscops. We are the weird, tiny-headed gut tanks, Cotylohynchus. We are even the small, furry, shrew-like cynodonts, the direct ancestors of mammals, scurrying in the undergrowth. Our side of the family rules Pangaea absolutely and totally. It is our golden age, and it seems like nothing can possibly go wrong. You are standing in the high, dry plains of late Permian Pangaea. The world is stable. The Synapsid dynasty, our dynasty, is at its absolute golden age. The saber-toothed Gorgonopsians are the undisputed apex predators. The great, warm-blooded, hippo-like herbivores are browsing. The world is in balance. It is the most complex and advanced ecosystem the planet has ever produced. And it is all about to die. We are at 252 million years ago. This is the Permian-Triassic boundary. And on the other side of the supercontinent, in a region we now call Siberia, a crack opens in the earth. This is not a volcano. This is not a cone like Vesuvius. This is a flood basalt eruption. You are witnessing the planet bleed. A fissure, 1,000 miles long, tears open across the land, fountaining curtains of lava miles into the sky. And it is not a boom. It's a roar. A deafening, ground-shaking, permanent roar that does not stop. Not for a day, not for a week. This is the Siberian traps. This is the mainstream historical fact of the Great Extinction. This planetary wound will continuously erupt, pouring out an ocean of lava for 1 million years. You are witnessing the planet's kill mechanisms being activated one by one in a cascading, unstoppable apocalypse. First, the atmosphere. The eruptions incoherently pump trillions of tons of CO2 into the atmosphere. But this is the quirky and absolutely devastating tidbit. The lava doesn't just flow over the land, it flows over the vast Carboniferous coal swamps that were buried there 50 million years earlier. The lava ignites the ancient coal seams. This bakes the coal, releasing colossal volumes of methane, CH4, a greenhouse gas 80 times more potent than CO2. The planet has just, in effect, strapped a methane-fueled afterburner to its own greenhouse effect. Second, the hothouse. Runaway global warming begins. The temperature of the planet soars. The global average temperature climbs by 10, 15, maybe 20 degrees. The tropics become lethal. The scientific evidence from oxygen isotopes in fossils shows that the surface temperature of the ocean climbs to 104 degrees Fahrenheit, 40 degrees Celsius. The oceans are no longer a habitat. They are a hot tub, a sterile global saltwater hot tub. Third, the acid. The volcanoes are also belching trillions of tons of sulfur dioxide. This mixes with the water in the atmosphere to create concentrated sulfuric acid. You watch as the skies begin to rain acid. A global, scouring acid rain that falls for thousands of years. The forests of Pangaea, the tough, dry land Glossopteris trees that feed the entire ecosystem, are stripped bare. Their leaves are burned away. The plants die. The land is sterilized. Fourth, the poisoned sea. The hot tub ocean can no longer hold dissolved oxygen. It suffocates, but it gets worse. In this new, hot, dead, anoxic ocean, a different kind of life thrives: anaerobic bacteria. Specifically, bacteria that eat sulfur and excrete hydrogen sulfide, H2S, a gas that is lethally toxic to almost all other life. The ocean, now dead, turns a sickening bright pink or purple from this bacterial bloom, and it begins to belch this poison gas out of the water and into the atmosphere. You are standing on the dying plains of Pangaea. The sensory experience is hell. The air stinks of rotten eggs, the hydrogen sulfide. It is so thick with toxic gas and low in oxygen that you can barely breathe. The sky is a weird, hazy, reddish purple from the sulfur and methane. The ground is a dead, grey mud, stripped of all life by the acid rain. This is the Great Dying. This is not an extinction. This is the extinction. The toll is a statistic that is almost impossible to comprehend. You watch as the world goes silent. 90 to 95% of all marine life is wiped out. 70% of all land life is wiped out. This is the closest life has ever come to being completely, totally, and permanently erased from the face of the planet. The Gorgonopsians, the saber-toothed kings, are gone. The head-butting moschops are gone. The armored Scutosaurus, gone. The entire dominant 60-million-year-long Synapsid dynasty is shattered. Our family's reign is over. And in the purple, toxic, hot tub ocean, the last of the trilobites, the creatures that defined the Paleozoic, the survivors of 3 other mass extinctions, finally give up. After 270 million years on Earth, their dynasty is over. This isn't just the end of the Permian. This is the end of an era. The entire Paleozoic era, a 300 million year long story, is over. The planet is now a silent, poisoned, empty husk. A new, terrifying era, the Mesozoic, is about to dawn on a graveyard. You are standing in the aftermath. The roar of the Siberian traps has finally quieted, but the world is a graveyard. This is the early Triassic, the morning after the apocalypse. The air is still thick, hazy, and low on oxygen, the sky a sickly chemical purple. The silence is what's most profound. There are no sounds from the complex ecosystems of the Permian. The ghosts of the Gorgonopsians and the great, warm-blooded herds of our synapsid cousins are everywhere. The world is an empty, hot, toxic dust bowl. This is not a world of complex ecosystems. This is a world of survivors. Paleontologists call the creatures that cling on in this hellscape the disaster taxa. They are the weeds of the animal kingdom, the scrappy, hardy, desperate few who managed to cling to life while the 95% were scoured from the planet. And in this empty, broken world, there is a king. You look out across the dead grey plains, stripped of all but the most pathetic, weed-like plants, and you see herds of them. Thousands of them. This is Lystrosaurus, and it is one of the ugliest, most improbable success stories in the history of life. It's a synapsid, our side of the family, one of the few surviving lineages. It's about the size of a large pig, with a stocky, barrel-chested body and short, stumpy legs. It has no teeth in the front of its mouth, just a turtle-like beak for shearing tough, dry weed plants. Its only teeth are 2 prominent tusks jutting down from its upper jaw, which it likely used for digging. This creature is the mainstream historical fact of the early Triassic, It is the survivor. But why? Why this one, pig-like, tusked, turtle-beaked thing? The scientific evidence points to a perfect survivor's toolkit for this specific apocalypse. 1. It was a burrower. Those tusks and powerful front limbs weren't just for digging up roots. It lived in burrows. When the world above was being blasted by heat and scorched by acid rain, Lystrosaurus was safely underground. It was hiding in its bunker, waiting for the worst of the chemical hellstorm to pass. 2. It had power lungs. Its barrel-chested, robust build suggests it had a huge, highly efficient respiratory system. Scientists still debate the specifics, but its lung structure seems perfectly adapted for a low-oxygen world. It was a high-altitude creature, born and bred on the high plains of Pangaea, and it was pre-adapted to survive in the toxic, oxygen-poor air of the Triassic, while other creatures suffocated. This one, ugly, burrowing disaster pig, didn't just survive, it inherited the Earth. And this is the single most bizarre and quirky tidbit of this entire era. You are looking at a monoculture. For a few million years, Lystrosaurus, this one, single genus of animal, made up 90% of all land vertebrates on Earth. Think about that. Go outside today. Imagine if every land animal with a backbone you saw, every bird, every squirrel, every deer, every mouse, every dog, every person, was just one kind of pig lizard. The planet was a post-apocalyptic B-movie world populated only by this one tusked, burrowing creature. It is the most unbalanced ecosystem the world has ever seen. But Lystrosaurus was not totally alone. Other, much smaller creatures survived too. Hiding in the cracks, surviving in the deepest, most remote deserts, were the other amniotids, the other side of the family. The Sauropsids, the reptile line. They were not the dominant Synapsids. They were the underdogs. They were small, lizard-like creatures, but they had two secret weapons that, in the Permian, were a disadvantage, and in this new Triassic hellscape, were a superpower. 1. They were cold-blooded. A warm-blooded synapsid is a high-energy furnace. It must eat constantly to fuel that furnace. In a dead, empty world with no food, a high metabolism is a death sentence. You starve fast. But a cold-blooded lizard? It can shut down. It can hide under a rock and not eat for a month, waiting for conditions to get better. 2. They were waterproof. Synapsids like us excrete urine. It's watery. We waste huge amounts of water every day just to get rid of our bodily toxins. But sauropsids, they evolved a brilliant water conservation system. They excrete uric acid, that white, pasty bird poop stuff. It requires almost no water to produce. In a hot, dry desert world like Pangaea, this is the single greatest advantage you can have. You are watching the changing of the guard. The great Synapsid dynasty, our family, is broken. We are reduced to one single, ugly, burrowing pig. And the underdogs, the small, scrappy, cold-blooded, water-saving sauropsids, they are looking at this empty, broken world, and their time is about to come. The age of synapsids is over. The age of reptiles is about to begin. The world is slowly, painfully coming back to life. The great dying left a wound so deep it will take 10 million years for the planet to recover. The atmosphere is still hazy and low on oxygen. The disaster pig, Lystrosaurus, has had its moment. Its 90% monoculture is fading as new, more specialized animals evolve. But what about our family? What about the Synapsids, the dynasty that ruled the Permian? We are broken. Our great mammal-like lineages are gone. The saber-toothed kings are extinct. The giant, warm-blooded herds are extinct. You have to look hard to find our ancestors now. You are in the undergrowth, at night. The Triassic is a hot, harsh desert world, and the new rulers are not us. You see a small, furry, shrew-like creature, maybe a foot long, darting from its burrow. It has whiskers, a wet nose, and big, nervous eyes. This is a cynodont. This is our direct ancestor. This is what our dynasty has been reduced to. We are no longer the kings. We are the shadow dwellers. We have become small, nocturnal, and secretive, hiding in holes, desperately trying to avoid the new masters of this planet. Our reign is over, because this is the Triassic takeover. This is the mainstream historical fact of the post-Permian world. The other side of the family, the Sauropsids, the reptile line, has exploded into the power vacuum. Remember their superpowers? They were cold-blooded, needed less food, and excreted uric acid, needed less water. In this hot, dry, empty desert world, those weren't just advantages. They were the keys to the kingdom. The Sauropsid line radiates, splitting into two major new groups. 1. The Lepidosaurs. This line will eventually produce modern lizards and snakes. They are successful, but for now, they are just small, scurrying, lizard-like creatures. 2. The Archosaurs, the ruling reptiles. This is the main event. This is the group that will define the entire Mesozoic era. But here is the most crucial plot twist. The Archosaurs themselves immediately split into two warring factions. Two great dynasties that will spend the entire Triassic in a battle for the planet. 1. The Pseudosuchia, the croc line. These are the winners. When you hear Triassic predator, you probably think dinosaur. You are wrong. Forget the lazy, swamp-dwelling crocodiles of today. These croc-line archosaurs are fast, upright, land-based monsters. You see one now. It's 15 feet long, weighs 1,000 pounds, and it is walking on two legs. This is Postosuchus. This is the quirky tidbit of the Triassic. The apex predator of North America is abipedal land crocodile that hunts like a T-Rex. It is Arauisuchian, and this entire family of croc-line archosaurs, the ornithosuchids, the poposaurs, they are the dominant predators. They are the kings. 2. The Avametatarsalia, the bird line. This is the Atheroside of the archosaur family. This is the line that will eventually lead to pterosaurs, the flying reptiles, who are already taking to the air in their own separate experiment. And another group. You see one of them now. It's scrappy. It's small, maybe 3 to 6 feet long. It's fast. It darts out from behind a fern, snatching a small lizard. It's light, hollow-boned, and it runs with an effortless bipedal grace. This is Eoraptor, the dawn thief. Or maybe it's Herrerasaurus, its slightly larger, more fearsome cousin. This is one of the first dinosaurs. And here is the key. They are not monsters. They are not dominant. They are not the kings. They are the underdogs. They are the small, fast, also-rans, living in the cracks, in the shadows, desperately avoiding the true rulers of the Triassic, the giant croc-line archosaurs like Prostosuchus. This raises the great question. Scientists still debate why the dinosaurs eventually succeeded. What was their secret advantage? They weren't stronger or bigger than the croc-line. They weren't faster. So what was it? The scientific evidence, which we infer from the structure of their bones and the air sacs we see in their later relatives, the birds, points to their lungs. The croc-line had decent reptile lungs, but the dinosaurs had evolved a super lung. It was an incredibly efficient, one-way, bird-like respiratory system. Air flowed through the lung, not just in and out. Why did this matter? Because the Triassic atmosphere was poison. It was a low-oxygen, post-apocalyptic air. The croc-line predators, like Prostosuchus, could give you a terrifying short burst of speed. But then they would be gasping, their inefficient lungs failing them. But a dinosaur, with its super lung, it had stamina. It could keep going. You are watching the state of play for the next 30 million years. The Triassic is not the age of dinosaurs. It is the age of the croc-line rulers. The dinosaurs are just the small, scrappy, stamina-filled pests living in the shadows, running circles around the real monsters. They are biding their time. They are waiting for the kings to fall. Awaiting continue. You are standing in the world of the late Triassic, 201 million years ago, and it is a world in balance. The planet has, for the most part, recovered from the Great Dying. The forests are green, and the great continent of Pangaea is stable. But it is not the age of dinosaurs. You know this now. You look at the landscape, and you see the true rulers. You see the Rauisuchians, the great croc-line archosaurs like Prostosuchus, the 15-foot-long bipedal land crocodiles. They are the apex predators. They are the kings. And the dinosaurs? You see one, a small 3-foot-long Coelophysis darting through the undergrowth. It's fast, it's agile, and it's prey. The dinosaurs are the underdogs. They are the scrappy bird-line archosaurs, living in the margins, surviving on their wits, their speed, and their stamina. That secret weapon, their super-efficient bird lung. They are a successful group, yes, but they are not the masters. The croc-line rules the world. It seems this stalemate, this dynamic of croc-king and dinosaur-scrapper, will last forever. The planet, however, has other ideas. You feel a rumble, a deep, ground-shaking, familiar rumble. You are about to witness the fourth mass extinction in the last 300 million years. This is the Triassic-Jurassic extinction. And the trigger? You look at the geological map of Pangaea. The supercontinent is under stress. It is too big, and the heat from the mantle underneath is too much. It's beginning to rip apart. You are witnessing the birth of the Atlantic Ocean. A vast, 4,000-mile-long rift is tearing the continent in two. And as it rips, lava pours out. This is the Central Atlantic Magmatic Province, or CAMP. This is the mainstream historical fact of the TJ extinction. It is another flood basalt eruption. Just like the Siberian traps, it's a great dying light. For 600,000 years, massive fissures erupt, fountaining lava, smoke, and gas into the sky. The kill mechanisms are, by now, horrifyingly familiar. 1. CO2. Spike. Colossal volumes of CO2 are pumped into the air. 2. Global warming. The planet's thermostat is cranked up again, suddenly and violently. 3. Ocean acidification. The oceans absorb the CO2, turning them acidic. This is a brutal, fast-moving apocalypse. The oceans are devastated. The reefs that had just begun to recover are boiled and acidified to death. The great conifer forests on land are scorched by the heat and acid rain. But here is the strangest, most fateful part of this entire story. The toll on land is selective. It's weirdly specific. The amphibians, the survivors from the Permian, are hit hard again. The Synapsids, our own furry, shrew-like cynodont ancestors, are decimated. We are driven even further into the shadows, our numbers reduced to almost nothing. But the archosaurs, the ruling reptiles, they face the real reckoning. And this is the great mystery. The pseudo-Suchians, the entire croc-line dynasty, the 15-foot-long Postosuchus, the bipedal land crocodiles, the Rauisuchians, the Ornithosuchids, the entire ruling class of the Triassic, are wiped out, vanished. And the dinosaurs? They survive. They are hit, yes. Many of their early families go extinct. But as a group, they sail right through the extinction, battered but intact. Why? Why them? Scientists still argue over this, the single most important lucky break in the history of life. What was their secret? Was it the quirky tidbit of their super lung? Did that hyper-efficient, bird-like respiratory system allow them to survive in the poison air of the extinction, while the less efficient croc-line predators just suffocated? Was their stamina the key? Or was it just dumb luck? Were they perhaps just smaller? Did their higher metabolism and possible warm-bloodedness, which was a disadvantage in the Great Dying, somehow become an advantage here? We don't know for sure, but the result is undeniable. The apocalypse ends, the CO2 is reabsorbed, the world cools, the air clears, and the dinosaurs, the underdogs, the scrappy bird-line survivors, lift their heads. They look around, and the world is empty. The kings are dead. The Postosuchus is gone. The Rauisuchian is gone. The entire dominant 50-million-year-old dynasty of croc-line apex predators is extinct. Every single large terrestrial predator niche on the entire planet is now vacant. This is the true dawn. This is the moment the before story ends. The dinosaurs, the lucky survivors, step out of the shadows. And for the first time, there is nothing to stop them. You are standing in a quiet, green Jurassic forest. The air is fresh. You see a creature step into a sunbeam. It's 10 feet tall. It has 2 small, delicate crests on its head. It's an early Jurassic dinosaur, a Dilophosaurus. It is no longer a scrappy pest. It is now the largest predator on its continent. It opens its mouth and lets out a deep, booming call into the empty, silent forest. It is a call that says, "This world is ours." The 4-billion-year, violent, alien filter of death that was prehistory is over. The 180-million-year age of dinosaurs has just, finally, begun. And with that, our long, long journey through the deep past comes to a close. The 4 billion years that it took to get from a ball of magma to a silent green ocean, to the invention of the cell and the first breath of oxygen. All of it seems to slow down. The terrifying armored fish, the giant, hawk-sized insects, and the saber-toothed proto-mammal kings fade back into their ancient, fossilized sleep. You can let go of the tension now. The apocalyptic fires of the Siberian traps are cold. The sulphurous purple skies have cleared. The great, empty, silent world of the Triassic has given way to a new, green, Jurassic dawn, populated by the survivors. It was a story of almost impossible odds, of 5 great resets that nearly scoured the planet clean of all life. But life, in its tenacity, held on. In the deep vents, in the frozen ice, in the dry burrows, it held on. And now you can just rest. You are safe in your own time, a warm-blooded, 5-fingered synapsid descendant of all that chaos. You are the improbable, breathing, thinking result of 4.5 billion years of war and ice and fire. You can close your eyes. The story is over. The silence of the deep past is settling. The world is hushed.